Hello, good morning, good afternoon, good evening, or whatever other time of day it might be for you. I am Michael Irwin from the DevRel team here at Docker, and I am excited to welcome you to the 7th edition of the Docker Community All Hands, the winter edition. We recognize that the holiday season is upon us, and so many of you are celebrating this time of year, so happy holidays. We hope everyone's had a great end of 2022 and is excited to recharge and spend time with family and friends as we all prepare for 2023. As we get this event started, we'd love to see and chat where everyone's coming from. What's the weather like where you are? Are you just starting your day or are you ending it? Are you new to Docker or are you a seasoned expert? Honestly, that's one of the things I'm most excited about with being as a part of this community is just seeing where everybody's coming from and learn from others. We're literally across the entire planet, and it's so fun to see all the different experiences from your. So feel free, again, drop in chat where you're coming from. Are you excited for it? What sorts of things are you excited to hear about and learn about while we're spending time together for this community all hands? We've got a great lineup of speakers and presentations spanning both today and tomorrow, covering a wide variety of topics, and we'll jump on that in just a minute. For those of you that have been here with us before, you might recognize that we're doing a couple things a little bit differently this time. First off, we're running everything here on YouTube. It's obviously a different experience than what we normally run with, but it is one that will hopefully be a little bit more accessible to more attendees. All you have to do is stay on this stream and we'll automatically go from one talk to the next. Like previous events that we've run, all of the talks are pre-recorded, so you're welcome to ask questions and ask for additional insights in the middle of each of the sessions, and the speakers will be able to interact with you live while their talk is going. Secondly, we've split the program across 2 days, so we're not just fitting this all into one day. We recognize with virtual events, people are still having to respond to emails or jump into work meetings and whatnot. So hopefully by splitting this across 2 days, we can accommodate more work-life balance. If you look at the calendar, day one is focused a little bit more on what's going on at Docker, some of the latest and greatest things that we're working on, as well as some of the neat things that others are building and are able to do because they're using Docker. One of the things there's actually two talks. It's both a kind of the first and last talk, kind of sandwiching the day. The first one that I'm really excited to hear about is actually from our friends over at NASA who use Docker as part of the DART project to be able to simulate taking satellites and crashing them into asteroids to figure out how we can change their trajectories. And there we go. It's a challenging word sometimes. Change their trajectories to literally save the planet. Some pretty exciting stuff there. And then the last talk, get to hear from the folks at Washington University on how they're using Docker and genome sequencing and everything to help cancer patients have a better chance of survival. Coming from the higher ed space previously myself, I'm super excited to see and hear how Docker is being used in the research space. So day one, again, we'll talk a little bit more about it here in just a moment. But day two is going to be focused a little bit more on workshops and actually hands-on. So if you're a little bit newer to Docker, day two is definitely tailored and focused towards you. And I'm excited again for those talks that are going to be coming tomorrow. Finally, we've tried to simplify things a little bit. You'll notice that we don't have as many tracks going this time with the community event, and everything's just a single track. Again, if you just stay on this stream, we're going to go from one talk to the next. Because of that, we're not going to have the regional locale specific tracks like we normally have had in the past. We recognize they're important. We want to be able to find ways to help you network with those that are closer to you. And we're looking at different opportunities to be able to bring those back. So stay tuned, and more information to come out soon. Now, before we get started, there are two popular questions that we get quite often that I want to answer right up front. Okay, so the first off is, are the talks recorded? Are they going to be shared afterwards? Yes. In fact, I just hinted earlier, the talks have all been pre-recorded, and so after the event, we're going to split them up into individual videos, and you'll be able to watch a specific talk very easily. So if you need to step away, answer emails, go to a work meeting, go get a meal, feel free to do so. No worries. Everything will be shared afterwards. Secondly, the most common question: how do I get some of that sweet Docker swag? throughout the event, what we're going to be doing is we're going to be watching Twitter. So use hashtag Docker community, all one word. So no dashes, no spaces or anything. So hashtag Docker community. Post on Twitter. What is it that you're learning? Maybe share a selfie with your viewing station, whatever you can think of. Share with the Docker community. And what we're going to do is each hour we're going to pick 10 tweets that are using that hashtag, and we'll send you out a voucher code that you can then use to go pick up a swag item from our store. So again, share on Twitter. We'll find you. We'll send you some swag. And so with that, let's get this party started, shall we? Our first speaker that we're going to hear from is actually our CEO, Scott Johnson. He's been a great advocate for the community. We're excited to hear from him, both the things that we've done in 2022, but also what we can look forward to in 2023. After him, we're going to hear from our friends at NASA, hinted at them earlier, and then a few different talks on Docker desktop extensions. Then we'll take a little break, and I'll jump in and share where we're going next. So with that, SJ, take it away, sir.
Hello, Docker developer community. Thank you for joining us in our winter edition of our Community All Hands. We estimate there's about 8,000 of you joining us from around the world, and we're so happy that you're joining us today for these 2 days of talks and sharing and just great demos. We want to start by just thanking you for this last year. It's been quite the year of 2022, and you have been so much of our success and our growth and our learnings. And there's lots of different ways to measure this, but here's a couple things to share. First off, there's now more than 14 million of you who are registered as Docker developers. You're coming from more than 230 countries from around the world, and you've developed almost 15 million container images and shared those with others up through Docker Hub. And those images are being pulled to the tune of over 16 billion times a month. And so a lot of creativity, a lot of innovation, a lot of sharing going out there. And we're so grateful for that. We also are grateful for how you've given feedback to us through other means. So for example, Stack Overflow, their survey this year, this is a survey about 70,000 of the Stack Overflow development community. You ranked us #1 most used developer tool, #1 most loved developer tool, and #1 most wanted developer tool. And again, we couldn't be thankful enough and appreciative enough because this gives us the feedback in terms of whether what we're doing here is on track to serve you and giving you what you need from a tooling standpoint, from a productivity standpoint, from a joy in your job standpoint. And that all gets back to our mission. Why we get out of bed every morning is to increase the time developers spend on innovation. And so surveys like this and the numbers we shared, that's giving us a signal that we're on the right track. Obviously more to do, but we can't thank you enough for that feedback. It's been quite a year in 2022, and so before we get into the 2 days, I want to do a quick look back on where we've come from and do a quick sneak peek of 2023 and where we're going. And so the 3 areas that we've shared with you all year long that we've been focused on this year are, first up, the developer experience in Docker Desktop. Second is providing you with trusted open source building blocks. Third, helping you take advantage of all the tools that are out there in the cloud native landscape that gives you the flexibility and choice of what you need for the right job. And of course, we reflect everything that we're doing in our public roadmap up on GitHub. And we invite you, if you haven't already, to go there, upvote your favorite feature, contribute a feature of your own. We're there, we're listening. Every single week we go through that and decide how to prioritize our efforts going forward. So first up, real quick, developer experience in the Docker Desktop. So often our industry has traded off speed for safety. If you're going to go fast, you're going to take risks, you might get in trouble. If you're going to really lock down and prevent any and all risk and 100% safe, you're never going to move. And so we see in Docker Desktop and the Docker developer experience the ability to do both, meaning you can go fast safely. In the last 12 months, we've been delivering a lot of features and capabilities to enable this. So on the productivity side, we brought Docker Desktop to Linux. In addition to Mac and Windows, now you have that same great Docker Desktop experience on Linux platforms. We completely rewrote Docker Compose in Golang from Python, and so now it's faster than ever before and integrates with your other tools. We've brought the latest and greatest features of Containerd into Docker Desktop. This includes productivity features like the lazy pull, so you can get started on the image as soon as it's coming down from a container registry versus having to wait for the whole thing to get down. We invested in file system performance in VirtIOFS, so you can make those iterations even faster on your local environment. We've extended the Docker toolchain to include operating not just on Linux containers and Windows containers, but now on WebAssembly objects as well. And so the same skills, the same tools, same investment you've made in containers, you can apply that to WebAssembly and take advantage of a really new, exciting, emerging technology in the cloud native space. We've also extended Docker Desktop. We announced this in May with the ability for partners and open source communities to extend the functionalities of desktop, whether that's the back end, the front end, the host side, with what we call Docker extensions. And there's now more than 700 Docker extensions available in our marketplace. We've also made it easier to find what you're looking for on Docker Desktop with quick search. So you can find the image, the stack, and get going and focus on your work. And many, many more features for productivity, but those are just a couple examples. On the security side, we've also made many investments here, and I'll share just a couple of them with you. First up, hardened Docker Desktop. This is enhanced container isolation, which brings another layer of protection to your environment. So if you do happen to download a malicious container and it tries to break out, it is stopped in its tracks. It cannot get over to the host side. It cannot break into your network. We've brought registry and image access management to the organization so that if you have a safe registry that you pull from, you can focus on that and not have to worry about random registries and random images coming in from the outside. We provided single sign-on, which many organizations use for centralized authorization and authentication. We've also enabled Docker Desktop to automatically identify and flag vulnerabilities that are there in your local images as well as images in other registries. These are just a couple examples, but it shows how together with productivity tools and security tools, we're enabling you to go faster safely. Now, this developer experience is available in Docker Desktop across all plans, both the free Docker Personal plan as well as the Docker Pro and Docker Business plans. And it's the same experience, and that's very intentional, that's very deliberate. And the way in which we keep Docker Desktop free is providing features that managers and security professionals look for when they're managing developer environments at scale. These are features like observability, manageability, and security. And these are features that large organizations need and are willing to pay for. And what that does is that allows us not only to accelerate our roadmap for features for all developers, but it allows us to keep Docker Desktop 100% free. And in fact, if you look across all the Docker registered developers, 13 million of you are using Docker Personal 100% for free. Docker Desktop and Docker Personal 100% for free. And a little over 1 million are using Docker Desktop in the paid tiers, the Docker Pro, Docker Team, Docker Business tiers. Now, the second area we've been focused on this year, these last 12 months, is trusted open source components, trusted building blocks, such as front-end load balancers or language runtimes or back-end databases. And in fact, we now have more than 500 publishers that are working with us to provide these trusted open source components through our 3 different programs: Docker Official Images, Docker Verified Publisher Images, and Docker Sponsored Open Source. And these are tools that developers use and need every day for building exciting, modern, new cloud-native applications. We've also been working this year on tools and standards to help make it even easier for you to adopt and use these trusted building blocks with your existing tool chain and in a way that's safe and assured for your environment. This is things like BuildKit, which automatically creates software bill of materials, SBOMs, and attaches it to the image so it can travel in its journey down the build tool chain. We now automatically create provenance that's in a salsa format that other tools can automate off of. Docker has become a CVE naming authority so that we're contributing to this community in terms of CVE numbers as well as notifications that all can benefit from. We've become an OpenSSF member, and we've also made Docker Hub 100% OCI compatible. So now in addition to containers, it can take Helm charts, Wasm objects, and anything else that's OCI compliant. Now, the third area we've been focused on this year is bringing you more and more tools from our ecosystem. We have over 450 ecosystem partners that are participating in this ecosystem, and we want to make it easy for you to use those tools in your everyday work. And that includes things like version control, CI and build. It includes container registries. And as I mentioned earlier, integration with the Docker Desktop to have a really tight, configured, secure environment with a choice across all your different tools. We're pleased that after the May launch of extensions in Docker Desktop at DockerCon, we now have over 700 partners, open source, commercial, and otherwise, providing Docker extensions for you up on Docker Hub. And again, this is a way that out of the box you can have tools that are configured, ready to go, so you can focus on your application and not focus on discovering, configuring, and setting up tool chains. So, Again, it's been a big year for 2022. Thank you for your feedback. Thank you for your feedback on the product and our direction. And we look forward to a 2023, which is also going to be quite exciting. We're focused on 4 big areas for 2023. First and foremost, perhaps no surprise, we're going to be doing even more for developer productivity, even more to help you go faster without worrying about configuration and low-level plumbing and infrastructure. We're going to do that not only for individual developers, but for teams as well. All applications are built with teams typically, and we want to enable an environment that helps you and your teams iterate very quickly and ship faster. Third, there's more to do on the software supply chain. This includes providing even more choice in terms of software building blocks across even more categories of software, as well as more tools to make it even safer and easier to bring these into your environment, use them safely, assemble a great application, and move it on, assured that it's safe and secure for others to use. And finally, ours is a very active ecosystem, new tools coming to market every month, and we want to make sure you have the latest and greatest there that you can take advantage of while you're building your next application. Now, all of this is publicly available, and we share in our public roadmap on GitHub. We invite you to jump in, upvote a feature, provide an idea for a new feature, help us understand, are we on the right track towards serving you? So I want to wrap up, and we'll get on with the 2 days here, but I want to wrap with a customer story. There's so many exciting examples of developer innovation that are using the Docker tools to create fantastic applications. We want to share this one with you. It shows really the power of developer innovation. Now, as we know, there's millions of asteroids out there circling our universe, circling our solar system, circling the Earth. And sometimes those asteroids look like they're on a vector to come, or on an orbit that could come close to Earth and strike it. And we know what happened to the dinosaurs. So NASA has a dedicated team that is studying this. They are tracking all the asteroids that are out there that are close to Earth, that could threaten Earth. And that team's charter includes coming up with plans and ideas to remediate. If there's an asteroid that's on track to potentially impact Earth, like what are they going to do? And there's a number of different projects out there exploring how to address that situation. Now, one of those projects, which has been in the works since 2015, is considering the following. Suppose an asteroid is on a flight in towards Earth. What if we could fly a satellite into that asteroid and divert it from its path and avoid it from hitting Earth? So they've been working on this since 2015, and all of the software to simulate and program the onboard computer and the software, all that's being done in Docker. And as the scientists have quipped, there's no rebooting in space. And so it's got to be right when it goes up there and tries to strike that asteroid. And Docker's been part of refining that software, testing that software, making sure it's going to work the first time. So under development for 7 years, this past September, it went up for a trial flight to see if it would work. And so after 7 years, it went up and it succeeded, which is very, very exciting. So let's take a look at a simulation of what that looked like. Pretty cool, huh? So whether you're a developer building a website, whether you're working on a mission-critical financial application, or whether you're programming a satellite to save the world, Docker is there to help you innovate. Thanks so much for joining us today. Hope you have a fantastic 2 days at our community all hands. We're looking forward to seeing you online, engaging with each other, engaging with the speakers. Let's have a fantastic conference. Thanks all.
Welcome, Luis Rodriguez. I guess I pronounced that correctly. Is it Spanish?
Yep.
Right. Cool.
Yes, you got it.
Cool. Yeah. So welcome to this interview. My name is Nelson. I'm one of the Docker captains, and I just want to really talk to you about Docker and how you and your company use Docker in your workflow. So do you want to start by tell us who you are and what you do?
Yeah, so I'm Luis, and I work as part of a team of flight software engineers on the NASA Double Asteroid and Redirection Test. And so this is a mission that it has, at this point, successfully demonstrated that humanity is prepared to deflect an asteroid if one were ever coming toward us, right? And that doesn't necessarily mean that there is one coming. There isn't at all. But we wanted to be able to test the technology, right? Just in case we are ever in a predicament where we do need it, to be able to, using pretty much just momentum, right? Like building a spacecraft, aiming it at an asteroid, and then hitting it so that we can slightly deviate it from its current course. Demonstrate that humanity can do that, and that we have the means to do it. And so, as part of the flight software team, I am one of a group of several that work on the, as we call it, the glue of the spacecraft. So we're kind of like we call it the glue, and then we also call ourselves the bit shifters, because what we do is grab bits of information from one instrument and kind of ship it over to another set of software that's making predictions on our current trajectory, or providing just housekeeping telemetry data and things like that on the status of the spacecraft, as well as commanding the spacecraft to do certain things, right, throughout the span of its mission. So in order to develop such a, rigorous mission, you kind of have to have a good development environment as a flight software developer. And hardware is not always available for you to test in. So back when we first started the mission, we decided to containerize using Docker all of the different components that make up what we call a spacecraft on a laptop. Mm-hmm. And so that spacecraft on a laptop is made up of the flight software component, which is what you load onto the spacecraft, the testbed software component, which is emulation software mimicking the functionality of, for example, like the radio or the camera that's taking images. And then being able to load, as a developer, load your flight software onto this still environment, still for software in the loop, that we call the spacecraft on laptop. And then just be able to run our test on, like, okay, am I configuring the camera correctly? Am I getting frames from the radio how I expect to get them? And to do that and be able to ship around that environment as easily as we could, we decided, let's use Docker and containers. And so that's kind of like the main way that we used it. And then what that facilitated was not only an environment for us to develop in and for us to test the flight software and the testbed software in, but also an environment in which we could replicate a developer's environment within a set of CI continuous integration pipelines. So being able to instantiate the spacecraft on a laptop, run a ton of regression tests, and then more or less assess, did we break it? Did we not break it? What we introduced, does it still work on another machine? Things like that. So that's like the main use of how we used Dockers and containers in Dart.
Well, that's quite interesting. So you see that picture there that I see behind you. Well, what is that?
Yeah, so the picture right on top is actually recently in September, the Dart spacecraft actually completed its mission of impacting an asteroid. And so as we were approaching during the last 4 hours of the mission, we're constantly taking pictures once a second of the target of the asteroid. And that is the last full all-encompassing image that we took of the Dimorphos, which is so our target was a binary system, which is just two asteroids orbiting around each other. Mm-hmm. The bigger one called Didymos, the smaller one called Dimorphos. Dimorphos is the one pictured there, which is the one we were trying to hit. And we continued to take pictures well past after that one, where you can kind of see getting closer and closer to the asteroid until you hit it, and then you completely lose telemetry. And so this is one of those few cases in space where you actually want to stop getting status telemetry from your spacecraft. You wanted to just say, I'm gone, right? So that was pretty exciting. And yeah, that's what that thing up there is.
Wow, that's amazing. So one thing that I'm quite interesting to know is, so let's just go a little bit back in time, right? So how was life before Docker for you guys?
Okay. Well, so before we started containerizing things and using Docker as our tool, and Docker Compose, right? Because we use Docker Compose as well to actually stand up all these stills. It was just kind of tricky to kind of maintain an environment where we could in a dependable manner instantiate our flight software and our testbed software and our little ground station so that we could replicate the SIL. So we would have to actually, first of all, we compile our code inside containers. So we have all our toolings inside our containers, and we just stand up a container and compile our flight software, our testbed software image, which is testbed software in C++ and flight software written in C. And so we before we had this constant back and forth of like, oh, it's compiling on my machine, but it's not compiling on yours. It's like, oh, do you have this dependency? Do you not have this dependency, right? The big question Docker has always tried to answer, which is like, it works on my machine, but it doesn't work on yours, right? And so that was the question we were trying to answer. And so we were like, okay, let's try and use a dependable environment, containers, right? Where I can just give you a container tag, and then you use that to compile your flight software image. So that was one of the problems we solved. And then the other problem was, okay, now you have a compiled flight software image and a compiled testbed software image, but you want to run them in a dependable manner, right? And you want to run maybe more than one of them, right? Like maybe I want to run multiple of these stills. And so these containers need to talk to each other. So we stand up a flight software container and a testbed software container. They talk to each other, and now we can have like different discrete versions of a spacecraft on a laptop. And so before we couldn't do that, right? Before we kind of were, if we wanted to implement this in like a continuous integration pipeline, we had to depend on our Bamboo agents to kind of just have all this set up already, have all the dependencies that they needed. Whereas with containers and Docker, we could just say, okay, we just need Docker on the agent, and then everything else is solved for, because we just give it the tags that we needed to use, right? The image tags. And so that became a lot easier to kind of keep everything packaged together. And when something did break in my machine and it was like, oh, it broke on my machine, but not on yours, the question was no longer, what dependency don't you have? It was typically just like, are you using the right tag, right? And so then you move your tag and then you're good, right? So yeah.
Right, cool. And in terms of, so if we take the asteroid example, so it took a picture in space. So if we take that scenario and then just try and see how would we test it locally. So what kind of stuff are you doing for testing all of your stuff?
Yeah. So the heavy lifting, so like the actual testing of the algorithms that do some of the guiding, for example, to the asteroid, right? Because as we're guiding ourselves, we're taking pictures and we're using the pictures, we're processing the pictures to kind of find centroids of where the asteroid is in space, feeding that into a navigation algorithm, and then it does the corrections. In order for that to happen, we usually test that on hardware, because there's like things like we had simulations, right, where because we don't actually have an asteroid, we had to kind of render these images of what the asteroid would look like, and then we had like a whole emulation for that. But most of that testing actually happened on hardware. The testing that is the closest we did to a completely software emulated environment was not really closed loop. It was more of for example, in order for us to configure the camera to the right settings, the detector and the telescope to the right settings to take images of the asteroid, you need to send commands to the flight software. A specific application within the flight software handles those commands and configures the detector. In reality, in an emulated space, so before you hop on a hardware testbed, you need to make sure you're doing that correctly, and you could do that in the SIL. So we could emulate what the detector configures itself to when you give it a certain command. And so that kind of testing we were able to do on the SIL, where I would, for example, implement a new command to set the integration time and the gain of the telescope for a specific test. And so I would go ahead and send a command to my SIL, completely emulated. The detector emulation would then tell me, yes, you configured me correctly, or no, something went wrong. And so we could do that testing on a completely emulated environment and then move over to the hardware where there was actually more of the pipelining required to configure the detector, and that part was tested for, so it should work on hardware. But then the rest of it, like, actually getting images and running our algorithms and all that ran on the hardware, because it was a lot more computationally intensive and required a lot more, just making sure that it works on hardware. So we that's kind of like one of the distinctions and one of the compromises that we knew we were making going into this, into this realm of using containers and things like that. Yeah.
Right. So if I was to, let's say I was to join your company, do I need to have a beefy machine in order to run these containers, or?
No. No, typically not. I mean, I think I don't think you need beefy machines. So most of the work that we did actually, because why not virtualize, right? So one of the things we ended up doing at first, we were working on our own, like off of our own laptops, right? So just like a Mac OS or whatever. But eventually we moved to having like Linux VMs, and nothing beefy, nothing out of the ordinary, just VMs that we could more, I guess, easily control in terms of the Docker setup. So like actually installing Docker and things like that.
Yeah.
And then we would run in those VMs, and those were never beefy. I mean, it's just like a normal laptop you could buy off the shelf, right? There's nothing crazy going on there, and no
interesting.
Crazy resources. It's just
cool. And in terms of the interaction of these containers, so you mentioned about Docker Compose. So how do you use Docker Compose in your workflow?
Yeah, so when we stand up our kind of emulated spacecraft, we are running flight software, testbed software, and the emulated ground station, all within within different images and on different containers, right? And so to orchestrate them coming up, we use Docker Compose, because we didn't need anything very heavy like Kubernetes or anything like that. We just needed something simple, and so Docker Compose was an easy way to go. One, because it was like within the Docker toolset, and two, because it was very easy to just stand up, write up the YAML file and then have your kind of like your container network set up for you and all that. So that's the way we decided to go. And the interface really is between like the ground station communicates to the testbed software container, which is emulating things like the radio, right? So you send a command from your ground station to the testbed software radio emulation, which is hooked up via a container, like container network. And then that produces, like, it sends a frame, like a command frame, over to the flight software container, which then processes that frame, and it replies with, like, say, a downlink telemetry packet. And then that goes to the testbed software radio emulation, which then talks to the ground software. So it's kind of like linear. The ground container to the testbed software container to the flight software container and back. And that was kind of our network setup within, and all that was done, right, orchestrated by the Docker Compose file and Docker Compose in the back. So
nice. So you've said obviously you don't need of Kubernetes. How does deployment works in your world?
So that's a very interesting question. Like we are unorthodox in that we don't really have like a deployment that we need to make, right? Like we don't have running instance of running, or at least in Dart, we did not have running instances of the SIL. We were just standing them up as we needed them and then shutting them down. So there was really no deployment. That deployment only went as far as, you update your flight software and you uprev a tag on the container image, and then that container image is ready for other people to use if they want to use it, right? But there was really no constantly running instance of the SIL that we then needed to switch in or anything like that. And I think that's what allowed us to use, I don't want to say primitive, but like simpler tools, because we didn't need to get that complicated for our use case. So yeah.
Nice, cool. And one question for you: what is your favorite feature on Docker that you absolutely love and you can't live without it?
That's a good question. I don't know. I like the simplicity of Docker Compose. Like I will say that there are other tools there, right? There are other containers tools. And I feel like one of the things that I've seen from, kind of poking at other container tools is that Docker Compose, the simplicity of Docker Compose and the use of Docker Compose is kind of not very fleshed out. It's either a really complicated tool or Docker Compose to me. That's, even when I'm exploring with other containers, other container infrastructures and, things like that, I usually end up using Docker Compose to hook up to, whatever it is, because it's just it's what I've grown to feel comfortable with. And I feel just an really easy interface. So Docker Compose probably.
It's just amazing how you could just spin up an entire environment locally, right? So you could tell me the same Docker Compose and I just run it and it just works. Instead of me having to know, I need this this plugin or I need this plugin, and then how do I connect them and whatnot. You could just write one definition how everything is connected, and off you go. I think it's one of my favorites as well, to be honest.
Yeah, and I feel like the chosen config file for a Docker Compose like YAML is also just very legible. So it was like a good choice to go with that, because it's like even if you haven't really used Docker Compose, I feel like reading a Docker Compose file is pretty self-explanatory. So I think that's also very useful.
Cool. And what are the next steps now for you in terms of what you're developing, and how do you see Docker affecting your development and moving it forward? How do you see the
future? Fortunately, in this case, our spacecraft is now dust and crashed into a space rock. So at this point, I think we're pretty much ramping down. With like we had our own private registry and all that, and all those things are kind of coming down, and we're just kind of keeping things for bookkeeping and things like that. But right now, I don't know. I know that there's new missions coming up, and new projects that we're all working on, and so moving forward, I know that we're considering different things in terms of containers and how we use containers. But one thing that is going to stick around is the use of Docker Compose again, and so we are maybe wrapping some of those things just because we want to make it as easy for the user as possible to kind of use Docker Compose, and we are moving towards a new workflow where a user is using Docker Compose, but we don't want them to know that. Like we want it to be completely them to completely be agnostic to it, in the sense of like they want to stand up a SIL, and we just give them the tools to stand up a SIL, and hopefully they have as little problem doing that as possible. So that was a long, weird way of saying I think we're going to continue to use Docker Compose to kind of to do our orchestration, because again it's limited. But in terms of like containers use and all that, I think some of these missions are still ramping up and things like that. So we're kind of doing our due diligence in what tools we use and what tools we don't. Nice. Yeah.
And is it Docker something which is widely used across the engineering teams, or is it mainly your team?
Say again?
Is it Docker used amongst the engineering team, or is it just your team that adopted Docker?
For Dart, it was mostly our team. Yeah, okay. It's just a flight software team, because our team is very multifaceted in the sense that we are like the software hub. But there's other teams working on software too. Don't get me wrong, like the ground software and the testbed software. But there's a lot of teams that work software, but we're kind of sitting in the center of like the spacecraft interfaces. So we decided to use Docker. Other teams like the hardware team, the thermal team, they don't use software, right? So they don't use Docker or containers or anything. So I think, APL, the Applied Physics Lab where I work, there's a lot of different projects going on where, we work in space, but we work on other things too. And I've had the opportunity to listen in on other projects and things like that. And I know that some of them use Docker, some of them use container tooling, some of them, so I know that it is used, but I don't know. I wouldn't be able to tell you how widely outside of just our specific case. So
cool. Listen, Luis, thank you so much for this interview. Is there anything that you want to say to the viewers?
No, I guess I would just encourage you, if you all haven't seen it, just go on YouTube or anything and watch like the last maybe 10-20 seconds of the impact video for the DART mission, because it was very exciting, and I think just history in the making, right? Hitting an asteroid. So go check it out if you haven't done that.
Cool.
It's pretty cool. And also, I will say in the DockerCon 2018, the flight software lead at the time gave a presentation about our use in Docker and gave a demo and all that. So I would encourage folks to go check that out too, if you're more curious about the actual details of how we actually use SIL and Docker and containers in Dart.
Cool. That seems an amazing field to look at, and we'll definitely make sure to share the links so that the viewers can absolutely see what you guys are up to. Cool.
Sounds good.
Thanks a lot, and I'll see you around.
All right.
All right.
Hi everyone, how is it going? How are you liking the community all hands so far? I want to see the comments in the chat. Good? Bad? What's your favorite talk so far? Well, in this session right now, we're going to be talking about what's the latest and greatest on Docker extensions, what changes had happened over the last months. And I'm joined by my colleague, Benjamin Randfont. Hi, Benjamin.
Hello, Alba.
How much did I destroy your name?
No, don't worry, it was perfect.
What a diplomacy here. Well, so Ben, he is one of the engineers that works in the extensions team, and I am realizing I haven't introduced myself yet. I'm Alba Rosa. I'm Alba, and I work at Docker. I'm in the part of the DevRel team. And I think it's a nice way of starting this presentation and this update would be to explaining, well, first of all, a little sentence of what Docker extensions are, if perhaps you're not familiar with Docker extensions. So Docker extensions, they basically let you use third-party tools within Docker Desktop to extend its functionality. You can basically connect your favorite development tools to your application development and deployment workflows. So it basically lets you augment Docker Desktop with debugging, testing, security, and networking functionalities, and build custom add-ons using the extensions SDK. But I think we're going to talk about all the latest in terms of like features and things that have happened in a bit. Ben is going to be in charge of that. By now, I'm just going to start with Docker extensions and Hacktoberfest. That's one of the biggest things that happened lately. I think the headline here for me would be that Hacktoberfest was a great deal for us. Thanks to Hacktoberfest, we got 39 extensions and 8 new ideas or proof of concepts that can potentially evolve into more developed and finalized extensions. It meant a 54% increase in terms of installs of adoption, so that was very, very positive. Let's also remind ourselves that Docker extensions was launched a few months ago, so it's not that it's something that has been there for a while, not at all. So I think it was like a nice push. One of the motivations we had to actually embrace Hacktoberfest and decided to move forward with that was because ever since we launched Docker extensions, there was a lot of community conversations, community requests asking us to implement certain extensions. So that's why we decided to actually pass the microphone on to them and ask them like, hey, what do you really want here? And you know, we offered you folks a space where you could actually show us what you had in mind and start coding yourselves a little bit on that. All over the month of, all over October, we had several meetups spread all around the world. We had, I think, around between 15 and 20 because some of them were before and some of them were after, so it's a little bit difficult to count here. But yeah, we had meetups in a lot of cities. I don't know. We had colleagues also speaking, like for instance, I don't know, in Madrid, in London. So it was really nice. And we had a landing page, and we got around 10,000 visitors to that landing page. So that was also something that I would like to point out. Some numbers here, right? But of course, this wouldn't have been great without our top contributors. These are just like our top 15 contributors. And yeah, Eduardo, Lalit, Sahil, Nitish, Mohammed Ali, Anik Harsh, Gangandeep, Leroy, Marcelo, Rizabad, Jijan, and Jason. Thank you so much for your inputs here. We've had contributors from all over the world. We've had contributors from Asia. We have contributors from Europe, America, So thank you so much for these contributions. These top contributors, spoiler alert, they got that prize that you see over there. It's like a macro keyboard with these customized caps. I think it's pretty cool. Once you receive it, please, let us know how swift is the experience of using Docker with it. But that's the good news. But I also have a little bit more of good news for those of you that are still asking us, like, hey, am I late for the party? I missed Hacktoberfest. Can I still join or participate in any way with Docker extensions? I have some ideas that I would like to share with the Docker extensions team. The answer is yes. You can actually still submit your ideas. Ben is going to tell you a little bit more in a bit about these extension ideas repo that we've launched. But that's actually the way where you could actually submit your contributions, and the best contributions are actually going to get swag. For instance, these keyboards that you just saw, we have a few left, and we are willing, of course, to share it with the best in class contributions. And I'm going to pass on the baton from here on to Ben, and he's going to be explaining what more community news for Docker extensions we have. Ben, all yours.
Okay, thank you, Alba. Well, let's start with the marketplace first. As you can see here, we have added the number of installs on each extension card, and also an option to sort by most installed. This allows you to see the most popular extensions on the marketplace. Lately, one of our focus was to improve the experience for extension builders, so we have added the Build tab here. From there, you can copy the Docker command to create a new extension, then just copy it, paste it in a terminal, and start build your extension. We have also included resources, the tutorial first, the documentation link, and link also to the publish form to publish your extension when you're ready to share it publicly. We have also added the community list of extensions curated by Collabnix and the Docker community forum where you can ask any question. In the future, we will add new content in this tab. Also, builders were asking us for a way to share their extensions quickly when not published on the marketplace. So we've added this share button available on unpublished extensions. And once you have pushed an image and a tag on Docker Hub, you can click on the button and it will copy the URL into your clipboard. Then what you can do is to paste it in a terminal like this, and it will directly open the detail page of this extension, even if it's not available in the marketplace. And from here, you can install it. There you go. The extension is here and it works perfectly. Finally, if you're not ready yet to build your own extension or want to share IDs, we have created a new GitHub repository, the extension IDs repository. From here, you can find all the extension IDs the community had or have. You can upvote for those that you think are the most interesting one. For example, the community's dashboard here, you can upvote it. And you can also submit your IDs if you want to just share an ID, or if you are seeking feedback for the one you have already thought about and you plan to build. And this is it for me. I hope you will have a great time at this Docker community all hands. And thank you very much. Have a good day.
Hi there and welcome to the Docker All Hands 7, and in this video we're going to be collaborating on the creation of a Docker desktop extension. We'll be taking a look at an awesome tool known as Hoppscotch.
If you are not aware of Postman and Hoppscotch, they are tools commonly used for interacting with the APIs. Super helpful for software development. Hoppscotch is completely open source, and we are going to build the Docker extension for this from scratch.
I'll be starting this off with the focus on Docker Compose and how we can actually run Hoppscotch as a self-contained application with Docker Compose. And after we've actually got this working, I'll then hand this back to Edie.
And we will show how to create an extension. We will initialize an empty extension. We will set this up for Hoppscotch. So we will get the structure ready, the metadata, extensions icons, and so on.
Then we'll combine these two efforts, the Docker Compose and the extension framework, and we'll create, hopefully, a fully working extension. Okay, so I'll see you in a few minutes, Edie. Okay, so for the first part, let's take a look at Hoppscotch.io. We're effectively looking to make this into an extension that we can conveniently have within Docker Desktop. That can be used anytime we're using Docker, so even if we were on a flight, doing local development, and had no internet access. If we take a look at Docker Hub and we do a search, Hoppscotch has an image there, and you can see this has had over 500,000 Docker pulls. If we scroll down, there's a lot of information, but we're interested in this. Let's just create a working directory and we'll go into that directory and we'll paste that command. Okay, so you can see that's running now on port 3000 and we can access this in the browser on port 3000 and also run the sample query that Hoppscotch provides. So that's working as expected. We'll just Control-C that for now. And let's create a Docker Compose file. Here we'll add the services, we'll add a Hoppscotch section. I always like to give a container name, the image, our port. At this point I'm giving this a high port here intentionally. And lastly, let's add some friendly usage comments and how to access. And we can do a Docker Compose up. That's running. It says 3000, but remember our forwarding port is 32433. And once again, we can access this in the browser and run the test. So again, let's Control-C that. We'll just clean this up for now. Okay, so with that bit done, I'm going to hand this back over to Edie to start creating the extension.
Okay, thanks James. So let's now take a look at extension creation. First, we will create a Docker extension skeleton. We will just fill in some details here. And we will wait for this to finish. Let's go to the Hoppscotch extension directory that was just created. This will create many things, but for us, we will keep it light. I'm going to take a look and get rid of some things. We can see that when we create this extension, it already initialized a Git project. We don't need the files generated in VM, so we will remove them. The metadata JSON is the main structure of the extension, so let's modify it so that it has the bare minimum. We will remove all these bits that we don't need. And we will save this file. We will copy an SVG file for the icon, and we will get rid of the old icon. And we will get rid of UI. We will keep this quite simple. And choose yes there. Let's edit the Docker file. And again, by here, we are going to simplify it. We will remove anything that is not necessary. And copy the UI directory. Lastly, I will update the metadata so our extension has a screenshot when we look at it. And we will change the icon to the Hoppscotch file. Now we will build the extension just to quickly test this. That's good so far. We will add a temporary web page for our extension. And we will install the extension. Choose yes there. Okay, so I got a problem. Let's take a look. Can you see it? This is the fan with JSON. Save that again, and we will try again. Oops, typo there in Hoppscotch. And that's better. And we try again. And all good. So this is our extension, now in Docker Desktop. If we click, we can see the hello from Hoppscotch. And if we choose Manage Extensions, we can see an example screenshot. Let's commit this to GitHub so James can add his Docker Compose efforts. We will create a new repository. Remember that the extension created a Git repo, so I will add this new repository as a remote. We will then add these files. And we will commit them. Okay, back to you, James.
Okay, so I'm going to fork Edie's project and just click the Create Fork. Whilst we're here, let's just add a default README and commit that as it is. Okay, great. And I'm going to copy the repository SSH reference. Let's clone that repo. We've got the repo and our Docker Compose file. Let's go into the repo. We can actually see we've got those files there. And let's check out a new branch for our integration. So I'll call this Add Extension and UI. I'm going to replace the skeleton extension Docker Compose with the one we created at the start. I've also got a template that we're going to use for the UI web page. This is just some simple HTML with an iframe to that port of 32433. So let's redirect that over the existing file. Now we can commit that, so 2 files, and we'll add both of those and commit that with a message and push to our branch. Okay, so I'm now over in GitHub, and let's select repositories. We'll choose the Hoppscotch extension. We've conveniently got a compare and pull request, so select that. I'm going to just put a stock comment in here and create pull request. Okay, so that's now back with you, Edie.
Thanks, James. So I am back at GitHub. We will choose pull request. We will open this app and merge pull request. Now, in the terminal, I can pull this to update the changes. We will build the extension again. And we will update the extension. Choose yes. Okay, that's done. And now, if we go back to the extension and click this, we've now got Hoppscotch running in Docker Desktop. Yay! And this is how easy it is to create an extension.
Okay, so that's it for this video. Thanks so much for your time, and we hope you found this useful and will be making your own Docker Desktop extensions. If you'd like, we've left the Hoppscotch extension open for contribution, and we're hoping to actually work with the creator of Hoppscotch, Lias Thomas, on the inclusion of this into the Docker Desktop extension marketplace. Thanks so much for your time and enjoy the rest of the Docker All Hands 7.
Hey there, welcome to Docker Community All Hand Events. Hope you are enjoying the show. Today I am here to invite some of the leading Docker extension publishers. Definitely this is a great opportunity for all of us to listen to their extension stories and see what problem they are trying to solve with these extensions. But before I jump into the conversation, I would like to take 1 minute of your time and brief you about the extensions. Now, if you have been involved in building a microservices architecture, I'm sure you are already aware of the moving pieces. It takes a lot and effort and time to understand how things glue up together, right? With the number of growing developer tools and that too being decentralized in nature, it becomes so much harder to install and manage and use these application services. And now that's where your Docker extension come into the picture. Now with extensions, your developers can integrate their tools right into the Docker desktop, which means that now your developers can seamlessly connect their favorite development tools into their applications and the deployment workflow. So with this, I would like to introduce our first speaker, Joyce Lin. She is a developer advocate at Postman. She has been working with the Postman for more than around 5 years now. And today she will be sharing her story about the new extension her team is building, rightly called as Newman Docker extension. Over to you, Joyce.
Thanks for that introduction, Ajeet. Let's jump into it. Postman is an API platform used by over 20 million developers around the world. There's a lot of stuff that Postman does, but there's one thing from the very beginning that the Postman community has absolutely loved. One feature is a crowd favorite. In the same way that containers are the foundational building blocks for the more advanced stuff that you could do in Docker, Postman has collections. That's the foundational building block for the more advanced stuff you could do in Postman. So what is a Postman collection? At its simplest, a collection is a group of API requests. Having a sequence of API calls allows you to write API tests, add documentation, spin up mock servers, and run your API calls ongoing or on demand. And organizing your APIs like this allows you to explore and share your work with others. So why run a collection in Docker Desktop? If you work with APIs, you know that there's a lot of stuff that you could do with APIs, whether you're an API producer or an API consumer. So today, I'll be sharing how you can automate your API tests and debug in Docker Desktop. Let's go over to the demo. I'm here in Docker Desktop. And if you go to the extensions marketplace, you can search for Newman. Newman is Postman's open source project that allows us to run these collections from inside Docker Desktop. So I'll install the extension. And once it's installed, you'll see the Newman extension here under extensions. So let's select that. And the first thing that we'll need is our Postman API key. This allows us to retrieve our Postman data, like our collections or environments. If you don't know where your Postman API key is, you can look under your Postman settings, but I should have this on my clipboard. So look away, pretend you don't see my API key, but once you have your Postman API key, Docker Desktop will remember your API key so that you can retrieve your collections environments until you log out. So let's retrieve our Postman collections. And now that I've authenticated with my Postman API key, I can access all of my Postman stuff. So I can select from the collections I have. I have one called test script examples. And if I have environments, I can run my collection against a corresponding environment. My environment might have configuration details about server environments or test users with credentials for certain profiles. So let me run my test script examples collection against my test environment and hit run collection. Depending on how long your collection is, how many requests, how many tests, how many scripts you have in your collection, this could take a while to run. But what's happening behind the scenes is that Postman's Newman is running all those requests and running all those tests. So let's take a look at the output. There's this HTML presentation that summarizes the collection run. So I see the total number of iterations, requests, some metadata. Here's a collection description in Markdown, timings and data, and a summary table at the bottom talking about my requests, scripts, tests, and assertions. So if I scroll back up to the top, I can also drill down and filter by total requests. You can see I have 25 requests in this collection. The number of failed tests, I have 16 failed tests, and skip tests if I have any. So if I go back to any of these filters, I can take a look at this folder, expand the folder, and select certain requests that were run, and I can see the request description and metadata. So this is the Markdown request description. Here's request information about the method, the URL, the response code, test pass percentage, request headers, cookies, request information, and also response information. I'm not sure what this endpoint is, but here's the request body, and if I want to take a look at it somewhere outside of Docker Desktop, I can copy the request body to my clipboard and do the same thing with responses. I don't know what this endpoint is. So now that we've run one collection, we can run another. Let's click run new collection, and maybe I want to run test scenarios for a logged in user or a non-logged in user, or run a collection with tests, or maybe I want to run against a different server environment. I can do that to my heart's liking. This one I think is a little bit shorter of a collection, so it shouldn't take as long. And here we go. I have 3 total requests, 4 failed tests, etc., and I can take a look at that. So one thing I do want to call out, it's very exciting to be able to run these collections in Docker Desktop, especially while I'm doing development. I can run these tests on demand, but some of the beauty of containers, I think this is a best practice, is you can recreate the exact environment that you want to be running your tests against. So Postman is, it's Postman's Newman. There's a very popular Newman Docker image that you can use to then recreate and run your tests against the test environment that you specifically want to be testing against. So let us know how you're using this extension.
Thank you, Joyce, for this amazing session. It was great to know that one can automate an API test and debug in Docker using Postman Newman's extension. As we talk about microservices, we know that these services communicate to each other through the endpoints, right? Now it becomes equally important for our developers to understand the behavior of each endpoint, whether it is slow, whether it is throwing some kind of an error. And that's where our next extension, Akita extensions, come into the picture. To take this discussion further, I would like to invite Versilis Tyson. He is a founding engineer at Akita Software. He helps his team create tools to make monitoring and observing system behavior accessible to any developers. He is based out of SFO, and today he is here to share his own story about the brand new Akita Software Docker extension. Over to you, Versilis.
If you're responsible for running a web service, you would probably want to answer questions like, what are my slowest endpoints? Which endpoints are throwing errors? What are my endpoints? that are still in use. Akita makes it possible to answer these questions without extensive setup or maintenance costs. All you have to do is let our agent watch your API traffic, and Akita will do the rest. With Akita's Docker desktop extension, we've made it even easier to set up Akita to watch your traffic. To start using the Docker extension, you'll need to sign up for our beta. If you haven't already, click here in the app to do that. To start traffic collection, simply provide the API credentials and project created during initial onboarding in Akita's web dashboard. Optionally, you can choose to filter traffic the Akita agent will collect by port or container. This will be helpful if you'd like Akita to only collect traffic for a specific app or service. After starting the agent, navigate back to Akita's dashboard to look at your first API model. Akita documents your API traffic exhaustively, which empowers you to have a transparent understanding of your system. Akita's dashboard provides an all-in-one solution for viewing your API models along with their corresponding metrics and errors. The main page provides a quick overview of your overall traffic amount, latency, and errors over the past week. For a more comprehensive view of your API models, navigate to the API Model tab. Here, you can look at your endpoints by amount of traffic, P90, and search your endpoints by path. To narrow down your search, you can also filter your endpoints by different kinds of properties, such as HTTP method, host, or authentication type. If you'd like to see your API models in a more standard format, click here to download the Open API specs generated by Akita. To view more fine-grained details, click on the endpoint that you want to learn more about. In this modal, you'll be able to view properties such as path and query parameters, headers, and request and response bodies. It looks like one of my endpoints is returning 404s that I didn't expect. For real-time information on the health of your app or service, we can navigate to the Metrics and Errors page where you can visualize statistics such as client error counts by endpoint. Let's check the 4xx count over the past week to see how this endpoint has been performing. With Akita, you can quickly diagnose API problems that would be difficult to detect otherwise. But what if you'd like to update the traffic Akita collects? If you'd like to update traffic filters or your targeted project, navigate back to Akita's Docker extension. Click on the gear icon, change your desired settings, and click Apply and Restart. Once the agent is restarted, click on View Container to check the status of the Akita agent. As I mentioned, we're in beta and would love for you to try us out. Akita will empower you and your development team to have a better understanding of your underlying systems. Give us feedback to help us build the API monitoring and observability tool you wish you had. To learn more about Akita's Docker desktop extension, check out the docs at docs.akita.software. If you haven't already joined Akita's private beta, click on the link in the app to request an invite.
Did you know that Docker extension also lets you to use third-party tools within a Docker desktop to extend its functionality? Sounds interesting? One of the most popular Docker Hub image today on the Docker Hub is Dive. This is a tool which helps you to explore a Docker image, layer contents, and discover a new way to shrink your image. This Docker image has been pulled 500,000 times from Docker Hub. So today we have a Prakhar Srivastav, a senior software engineer working at Google, who built an extension out of his curiosity. Today he is here with us to show how he built a dive-in Docker extension and how it is useful for the developers. Let's hear from him.
Thank you, Ajeet, for that introduction. Hey everyone, I'm Prakhar, and today I'm going to be talking about an extension that I recently wrote for Docker called Dive-in. Now, Dive-in extension is built on top of an excellent CLI tool by Alex Goodman called Dive. So let's spend a couple of minutes talking about what Dive does, and then we'll jump back into the Dive-in extension. So Dive is an open source tool which is extremely popular in the open source in the Docker community, as you can see from these stats. But primarily its main job is as a tool is to help users explore a Docker image, its layer contents, and discover ways to shrink the size of the Docker image. Now Dive is primarily a CLI tool, and that's the only interfaces it offers. You can invoke Dive right from your CLI on an image that you have locally, and it will tell you some of its contents, its efficiency, where the space is getting used, etc. For some people this might be totally fine, the CLI interface, but for some this can be a bit cumbersome to navigate. And so what Dive in extension does is basically presents all this information in the Docker extension. But before we jump to that, there's one other cool thing I want to point out about Dive, which is this idea of the CI flag. And what this allows you to do is, if you want this kind of a analysis or a check in your continuous integration pipeline, then the Dive tool can be really helpful. So if you can see here in this screenshot, it analyzes an image and it gives three main stats, for example, efficiency, wasted bytes, and the user percentage. And then it either passes or fails an image based on the thresholds that can be set by you. And so this is extremely useful in a CI pipeline, where before deploying an image to production, you want to make sure that it passes kind of a size threshold. And so this is very helpful in setting that up. So let's jump to Dive in. So like I said, Dive is built on top of the Dive tool, and it provides all the features that does, except the CI flag, except the CI option, which obviously does not make sense because Docker Desktop is meant to be run locally on your laptop during development. So let's now switch to the Docker Desktop and see what Dive in, what the interface looks like. So let me quickly switch. Okay, cool. So as soon as you boot up Dive in, it lists all the images that you have locally in this nice layout grid. So all you have to do to understand the image is basically just click on an Analyze button. So I can click the Analyze button for the Getting Started image by Docker. It should take a few seconds, and once it's completed, it shows me the stats here. So like I said, this is the same data that you would get from Dive, but presented in a slightly easy to use UI. So you can see here, it gives three main important bits of information right at the top. And this is what Dive uses for passing or like failing a check in the CI setup. And so as we can see here, the total size of the image, the inefficient bytes, and the overall efficiency score. It also shows what are the largest files sorted by the size. So this is a good way to know what files are taking how much space, and if you want to start diving into where can I reduce images, this is a good starting point. It also shows what are the layers. Now most of you might already know a Docker image is made up of layers stacked on top of each other, and every layer adds some space, consumes some storage. And so you can see here that it gives you all the layers that are used in building this image, the size of them, and what sort of command sort of added that layer. And again, this is also very helpful in diving deep into what are the number of layers. The number of layers is very important when like pushing and pulling from Docker Hub or any other artifact registry. So all of this information is really helpful and important in figuring out the overall size and where and where the usage is going. So let's go back to images, and you can again try another one from this list here. One thing I want to point out that the amount of time it takes for the analysis is strongly proportional to the size of the image. For larger images, since the layers are larger, the number of files that has to analyze is much longer. So if you've noticed, the first image was just 30 MB and this is like 112 MB, so almost like around 3 times, and it took slightly longer. So in this case, you're analyzing the Redis image, and you'll see here the total size of the image, the inefficient bytes, and the efficiency score. And again, it's the same data visualized in a nice table where you can see the total size of the main files in this image. You can also go down and you can see all the layers in the image. And that is mostly it. I would like to encourage the community to try out this tool, and if there are any issues or feature requests that you have in mind that will make this tool better, feel free to create an issue or submit a PR, or any kind of contribution is extremely valuable. And thank you so much for having me.
Okay, with this, we are towards the end of the session. I would like to thank each of the speakers for their time and effort. Thank you so much for watching us till the end. If you are building an extension or want to share some ideas, feel free to visit docker.com/extensions-ideas. This is a discussion forum that we use to collect suggestions for a new Docker extensions. Don't forget to upvote ideas which you'd like to see. Thank you again and have a great day.
Hello, everyone. I hope you've been enjoying the Community All Hands so far, and I'm excited to have here with me Javier, who's doing some pretty incredible things while we're going through these talks. And Javier, what are you doing? What you doing for us?
Oh, this is quite simple. This is called graphic recording, and it's just taking notes impromptu, trying to take notes about all the concepts that resonate with me from the talks, and that's all. It's quite easy. It's not rocket science.
Yeah, you say it's not rocket scientist, but for somebody like me that they can't draw very well, it feels like rocket scientist at rocket science at times.
Everyone can draw.
Yeah, it's so good.
Yeah, sure. Let's do it.
Very cool. Yeah, and it's so neat how you represent everything, and Javier here is going to continue working on these graphics for us and taking notes for us throughout the rest of our day today. And we'll talk more about it at the end of our hands-on. And so stay tuned for more. We'll be releasing all this to everybody.
Imagine a Docker image that only contains a single binary of your app. Then imagine if it can run on any host without having to rebuild a new architectural image. Oh yeah, and it's also smaller, way smaller, by sometimes order of magnitudes smaller image. It starts faster, it defaults to higher security guarantees, the list goes on and on. But imagine that future for a second. So in this talk, we're going to cover what is cloud native WebAssembly and how is it different than the WebAssembly you maybe heard about years ago, how Docker is innovating in this space, and how you can get started. Let's do it.
Hi, I'm Nigel Poulton. I'm a Docker captain like Brett here. I've been working with Docker and containers and Kubernetes since for like too long, but now I am in the weird and wonderful and crazy and scary world of WebAssembly, or sometimes as we call it, Wasm.
Hi, my name's Brett. All right. We're talking about Wasm. What is the origin of WebAssembly?
Although it had nothing specific in its like initial specification and implementation that specified it had to be for the web, despite the fact that it's in the name, right? Web and assembly. It's neither web nor assembly, actually.
Perfect.
But obviously the first major use cases, were in the web. And I think the idea, and I'm careful how I say this, but I think the idea was that JavaScript, let's just say, had its challenges, still has its challenges, and that there was a way to kind of do applications like that in a better way. So originally, when it was first implemented in a bunch of browsers, people were thinking like, is this going to be the JavaScript killer? Obviously, that never happened. So WebAssembly itself is its own bytecode, which look, for all intents and purposes, is almost like its own machine code. It's like an intermediary layer, actually, but it cuts out some of the steps when you're compiling JavaScript apps and things like that in a live environment. Going from your code to an executing application is much quicker with WebAssembly, which is why WebAssembly tends to be the go-to solution if you're like creating high-performance web apps. Was it 2017 or something like that we first started hearing about WebAssembly? And it was your likes of Mozilla and Google and Apple and people like that were all behind it, which are web giants. And I guess then it's no surprise that its first implementations were in the web. So WebAssembly did a really good job on the web of making applications faster, while at the same time being secure and portable, because everything on the web has to be secure and portable. Yeah, and a bunch of people saw that and they were like, oh, I tell you what, I'd like to build some cloud platforms that have got some of that goodness in it. That's the origin story according to me.
Yeah, so if we're talking about it's running on the server, are these binaries that we're building? Is there something else involved with, if I decide to take a Node.js app or a Python app, because I hear that there's all these languages now that you can make into Wasm binaries. Before Docker, like what would normally be on a server before, so I could run one of these new Wasm things on a server?
So to run a Wasm app on a server, you need a Wasm runtime. So you take your code in whatever your favorite language is, right? And don't get me wrong, not every language can do this yet. The list is growing. It's not as big as we would like it to be. It never is, right? But more languages are coming on board. And when I say on board, it's the ability to take your source code and instead of compiling it for Linux on whatever, ARM64 or Windows on x64, whatever, you can now compile it to a Wasm binary because it's its own bytecode, really. Okay. But in order to run that, you need a Wasm runtime. And there's a bunch of them out there. Probably the most famous one, it's the bytecode Alliance reference implementation, actually, but Wasm time. You can run it on Windows, Linux, Mac OS, probably others as well. And as long as you've got that, you can take that Wasm binary that you've compiled from your favorite programming language, just execute it like it's a normal application. And you get near native speeds from it as well. In fact, I have heard some instances, and we can maybe come back to it later under performance, where you can potentially get better than native speeds. And I remember the first time I heard that, I was like, better than native? What? You're pulling my leg, right? How is that possible? But yeah, basically the story is you take your code, potentially at the moment, a typical microservices application written in whatever languages. If that languages compiles down to Wasm, great, do that. And anyway, you've got a Wasm runtime, bingo, you can run it.
The nice thing is, those of us in container land, we know about runtimes because when we're running a container, we're used to having something on the server. What did Docker do that sort of helped out the Wasm community?
Okay, there was a project in the community called RunWasi. I believe it was created by the guys at Deis Labs, acquired by Microsoft recently. By the way, I like a lot of what they're doing in the open source space. But this RunWasi it's a containerd shim. And what it lets you do is, say, you can even have a Kubernetes environment, right, that's scheduling workloads. And it schedules workloads to a node. There's a kubelet on the node, and the kubelet will say to its container runtime, which quite often is containerd, hey, run this piece of work for me. And we know that containerd usually has a shim, and then it uses a low-level runtime called runc, quite often, out of the box, that's your default, to actually execute the workload. However, from like Kubernetes perspective and even Docker's perspective, almost everything below containerd is opaque. Like you can swap out runc for a different runtime. And because it's opaque below containerd, there isn't really anything stopping containerd executing WebAssembly workloads. And in the architecture, you've got Docker Engine scheduling work to containerd saying, hey, start up this particular work task for me. If it happens to be a WebAssembly work task, then it calls the containerd, the RunWasi shim, which sits in between containerd, and then in this example, it will be Wasm edge at the bottom, which is just a WebAssembly runtime. So look, RunWasi sits between containerd and abstracts like the low-level sort of Wasm runtime machinery from containerd. So containerd really doesn't know that it's running a Wasm workload versus a container workload. It's just saying, start a piece of work for me, stop a piece of work for me, delete a piece of work for me. The RunWasi shim lets us plug in a Wasm runtime into those kind of environments. Now, what Docker did was they took that RunWasi shim, took a fork of it, and they made it so that a particular WebAssembly runtime called Wasm Edge would work with containerd. Now, look, since then, this RunWasi project has been voted in as an official containerd shim. So it's now been upstreamed into the official containerd. Really good stuff is happening there at the moment. And that's very much thanks to the Microsoft Deis Labs people, Second State, Docker, people like that, not only investing like developer time in it, but including it in their tools and things like that so that it's getting more use, it's getting out there. And I dare say, look, Containerd with the Runwazi shim is looking very much like the most likely route to getting WebAssembly workloads on Kubernetes going forward as well.
Okay, so given all that, when should we be looking at WebAssembly for cloud native?
So this is where we get into like the realms of it's super early days with this kind of stuff. And you'll remember, and a bunch of people watching this that were in early with containers, is that there was, you're always battling with that appetite to run as much as you can on it and push the boundaries when maybe the tooling and the technology isn't quite there yet. And we did a bunch of that with containers and with Kubernetes, but they've matured a lot more. I feel like we're very early days with this. So right now, WebAssembly workloads have outrageous cold start times. So that makes them like super good for event-driven, like function as a service type things. But also because the binaries that they produce are so small and so efficient, then they're also a great choice for anything that's like out on the edge where maybe you're resource constrained. I would say that at the moment, right, yes, you can get away with running other workloads on WebAssembly, but I feel like you're going to be hacking a bunch of stuff together in order to do that. And it just feels like, for the meantime, outside of that event-driven function as a service type model, or maybe out on the edge, containers is really still the go-to model for everything else, because not only are the core technologies baked and understood, but also the developer ecosystem, all the tooling, the support from third parties and things like that is there.
That brings up a good point. What's in the image that I make? So if I take your Rust app you talked about, normally with Rust people, we would build a binary, right? A Golang would have a binary. And we're used to in those worlds of having a very small image because we maybe don't even need anything other than those executable binaries. They're built for Linux or for Windows or whatever. A lot of us are still in Node.js or Python or Ruby or whatever, and we're adding often many thousands, if not tens of thousands of files with all our dependencies. I will look at some of these apps like Ruby apps and Node.js apps, especially with the default built-in base images, and there'll be 200,000 files in that image. So how does Wasm improve on that?
Let me compare it to just a traditional app in a container, right? So we would start with a Docker file and you would have a base image. And that base image has got a bunch of, let's just call it a minimal operating system. Most of us probably know this, right? It's got a bunch of file system structures and things like that. And then you copy in your code and you pull in a bunch of dependencies and things like that. You end up with kind of this layered model with all this stuff in there. This is very different to that. There is no real concept of saying we need it to package a minimal operating system with it. Now, look, this may change, but right now, when we're like writing HTTP handlers and things like that, basically you're just taking not a lot of lines of code, and I'll just use Rust as an example because we're going to see it later, and you just compile that down to a release binary. So I guess a lot of languages will have a way to compile like a release version of a binary that's basically got all of the debugging tools and things stripped out, and you take that binary as a WebAssembly binary and you just run that. The WebAssembly runtime provides everything that's necessary in order to execute that. So Docker have done a really good job recently of folding WebAssembly into our existing tool sets and our existing platforms and things like that. So instead of having to like get rid of all of the tools that we've used in the past and learn everything from the ground up new, not only WebAssembly here, but a bunch of new tools and new platforms and things like that, Docker are doing a really good job of saying, look, we've already got great tool chains here. We've got a great registry and all of that. And adapting those tools to work with WebAssembly. Now, if you do that, current way at the moment is to take your WebAssembly module or your WebAssembly app and package it as an OCI container. Of course, Docker does that. We'll see a little bit later in the demo. But to do that, it starts from a scratch base image because you need to do that in a Docker file just to build it. But once it's wrapped in an OCI image, then you can host it on Docker Hub or somewhere else where you can then use Docker run to run it, all of that kind of jazz.
Yeah, you and I were at KubeCon, and Kelsey Hightower from Google met with the CEO of Docker, SJ, and they had a fireside chat, they called it. And I loved it because it was It felt like it was a conversation about Wasm for mere mortals. And of course, Kelsey does what Kelsey does. He always breaks down the myths and the hype. And one of the things he really pointed out that we've made all these deployment pipelines with containers now. We've all spent the last close to 10 years now building systems to deploy images using all the standard OCI specs that we all now know and love. And that by Docker taking this route, having containerd bring this in as a shim, it basically allows us to use everything we already have today for this new type of binary. Because they could have just said, let's just ship a runtime in your image with your app. That's essentially, to me, as a Node.js or a Ruby developer or a PHP person, that's what we're doing. We're all just shipping the runtime with our source code. I like it how it flips it on its head and says, we're going to handle the runtime, and you just ship your bytecode that sort of, I think of it as like a middleware, like it's this middle layer that is efficient. Like you said, it's super small because it's not including hundreds of thousands of files. It doesn't have to have all these image problems that we've dealt with, especially like we talked a lot about DockerCon, where we talked about images having all these vulnerabilities in them because of all the unnecessary files like package managers and curl and shells and all these other things that maybe you don't need in the container, which spawned this whole other industry of how to reduce image size. Well, if there's only one Wasm binary in my image, like it's not going to get any smaller than that. So I look at this as a win for us operations and DevOps people as well, because granted, it's going to be up to the developer probably on whether they decide to do Wasm. But if they're going to ship it to me, I'm going to be able to run it. So let's get to the next part, because I feel like for people that are now grokking a little bit of what WebAssembly is for container native, they're probably asking, how do we do it? What's my first steps? If I'm interested as a developer and I'm already got Docker desktop, what are my next steps?
Yeah, so I suppose you need to make sure that your languages that you write your apps in support compiling down to WebAssembly, because really WebAssembly, at least the way that we expect to use it, isn't as like a new programming language. Yes, you can do it like that. But generally speaking, we're going to take things like Rust and Go and Python and stuff like that and say, we're going to keep writing in those languages, and it compiles down to WebAssembly. So I think that's your first step. Does your language support compiling to WebAssembly? After that, you need to decide, look, if you've already invested in Docker and Kubernetes and things like that, it is probably a good way to go because you've made an investment in a platform and things like that. It's pretty early days still at the moment. So a lot of this stuff is going to be in beta or tech preview for a bunch of this kind of stuff, maybe for a little while.
And so Docker announced Docker Desktop supporting Wasm at KubeCon. What does that do for us in Docker Desktop?
As soon as you've got a WebAssembly module or a WebAssembly binary, you can write a Docker file that will wrap that in a container image or an OCI image. You can then use Docker push to push it to Docker Hub. You can use Docker run to run it. And basically, you're then, it's almost as if it's not even a WebAssembly app, other than the fact that you get a bunch of the benefits of WebAssembly because you're just using the tools that you use every day.
And that's specifically a Docker Desktop thing right now. Like I'm guessing that Containerd eventually will have an ability for us to run this in Kubernetes.
That's right. And I think Ralph's probably going to talk about it in his Azure session a little bit later, but just to tee Ralph up if he does. So Azure Kubernetes Service, AKS, already has in preview the ability to have Wasm node pools in an AKS cluster.
Okay.
And they use that exact same run WASI containerd shim. And you just define a runtime class on Kubernetes for those node pools, and anytime you schedule a Wasm workload to Kubernetes, it will schedule it to those node pools, and they use Containerd to do that high-level scheduling. Containerd has the run WASI shim in there that then uses Wasm time or others in the future, that kind of low-level WebAssembly runtime to actually execute the work task. So it's already, I'm not going to say it's here for Kubernetes because as we speak, that's in tech preview on AKS. But believe me, this stuff, for me at least, it feels like it's coming fast.
All right, given all that, will Wasm take over the world?
I feel like I should do an evil laugh for that. Look, I think in as much as VMs took over the world in their own way, in their peak, and that containers have taken over the world and potentially haven't even reached their own peak yet, then I don't see any reason why WebAssembly can't and probably won't take over the world the same way that those two have. Like for now, like we said before, it's a bit niche in that it's got some use cases. And outside of that right now, you're just putting yourself into a world of hurt if you're trying to make it do everything else. But I don't know, I feel as the core technologies evolve, and then as the ecosystem grows around it, just because like containers, it's smaller, faster, more secure, and more portable than the previous generation technology, I don't see why it won't become the dominant model like VMs did and containers are at the moment. Now, look, is it going to take over the world and replace everything else? Of course not. Nothing ever does. Not even containers. Like even in the kind of height that they're in at the moment, we've still got VMs.
So you and I were actually having a conversation before we recorded this, and we were talking with the Docker team. And one of the questions I had that they had to answer for me was, is this different than building a Wasm app for the browser? And the answer I got back, thank you, Michael and team. The answer was like, if you're not running on the server, you don't need this separate runtime, because if you're running in a browser, the browser's the runtime. So if you're a web developer today, this doesn't really change what you're doing for making web browser-based WebAssembly apps, because Docker still could be a great tool for that, like all web development, and you're still going to have your tooling that builds it into the binary that then hosts it on the web server. But what we're talking about here is the other half of that, the things that aren't in the browser, which will need a runtime and some of this tooling in the middle. And why not take advantage of the existing pipelines and all of the container and image stuff that we already have with the OCI spec? All right, so the way to get started is you first need to have Docker Desktop 4.15 or newer, then go into settings, and you're going to enable the Wasm beta in there. Secondly, if you want to get some of the documentation on it, you have a couple of choices. One is Nigel's post that he mentioned before the demo. That's right here. And that is over at nigelpoulton.com. And then secondly, you can go to Docker's website. And if it's still here when you watch this video, if you hover over their logo and click the Wasm under their logo, it'll take you to it's a shortcut to the desktop/Wasm page over on the doc site. And then you can go to Docker forums, which now have a dedicated section in the Docker forums. That's forums.docker.com for questions about WebAssembly in Docker. And they have a whole new topic there.
I think the idea of this demo is just to give us a 40,000 view of what the steps are, the process, some of the tools. That's it really. And look, anytime you learn a new technology or a new programming language or whatever, we've always got to do a hello world, right? It's a rite of passage.
Yeah.
So from the perspective of a demo, I've got two prerequisites that if you want to follow along, you're going to need yourself. You will need the latest version of Docker Desktop. You will also need the Rust programming language installed. And with those two, the only other step that you would need is to add the Wasm32 WASI target to Rust, which is basically just enabling Rust to take the source code that we're going to write and compile that down as a WebAssembly binary. So look, I'm rubbish at typing, so I'm going to copy and paste commands here. So first command is cargo new hello Docker. That's just going to scaffold up a simple Rust app for us. And within that, it creates a bunch of files and a folder structure and stuff like that. But the only one that we're interested in is the main.rs file here, which, as we can see, is a super complex hello world app. I'm going to be brave here and go all cutting edge, and I'm going to change it from hello world to hello community all hands and save that. So look, it's
Star Trek nerds, so yeah.
It's got to be done. So actually, when we run the app, I'm expecting the same from you later on, Brett. But look, it's going to print some text to the terminal, right? Very advanced. Once we've got that source code written now, how easy was that? All right, so from within the directory of the application, if we do a cargo build, the -- target wasm32 WASI just says to Rust, instead of compiling this down for Intel on Mac OS, which is what I'm currently on at the moment, don't do that, but create this instead, or compile this as a WASM32 binary. And then -- release just says, don't include debugging tools and stuff like that, make it super efficient. Bingo, and look at that, it's done. So now that we've got the Wasm binary, I guess we could run that right now just using Wasm Time or Wasm Edge or something on my local machine. But I really want to package it in a container image so that if we wanted to, we can push it to Docker Hub and then use Docker Run to run it later, which is actually what we're going to do. In order to do that, we need a Docker file, which I have got in the local directory here. And if I just show you the contents of that Docker file, super simple, right?
Doesn't get much easier than that. It's from scratch too, right?
Exactly, yeah. So the scratch image here as a base image is really just so that we can use Docker build to actually build it. That base image or anything doesn't get used for anything. It's just, it ends up being an artifact of the build process here. All we're interested in is the middle line. This is going to copy in WebAssembly binary on the end here and then set the entry point to that. So the command to run or the application to run, when we come to run it, when like it's all unpacked out of the image and comes to run, it will run our WebAssembly binary. To do that, I am going to copy and paste a docker buildx command, which is basically saying build, set the platform for the image as Wasm, give the image a name, and build from the Docker file in our local directory. Fingers crossed and offerings to the demo gods that this works. Okay, fabulous.
So the only thing different there was you just had to add the platform, the -- platform, which technically isn't a new one, right? Like we've had that -- platform for years now. For you to specify ARM, if you're on Intel and you want to build for an ARM machine, you can specify the platform you want to build for, and that's a feature of BuildKit and the buildx command. So we're just seeing Docker extend this out to a yet another type of runtime or another target, a build target.
Absolutely, yeah. Right now, I think all it's potentially used for is if the image is then pushed to Docker Hub. So somewhere in here we go, we'll see that the OS is set to WASI, and the architecture of the image is set to Wasm. And that kind of stuff can potentially be leveraged heavily by Docker going forward. Okay,
Ooh, I have a good question for you real quick. What is the difference between WASI and Wasm?
Okay, WASI is the WebAssembly Systems Interface. It's an interface for allowing WebAssembly apps to be able to access more like server-side resources. Because I think we've probably talked about this before, that look, WebAssembly apps in a web browser need access to totally different things than WebAssembly apps that are running in cloud servers, like access to the network and access to the local file system and things like that. That kind of stuff is still being baked, and WASI is the API or the way that WebAssembly applications will access host resources.
Yeah, so that means, so WebAssembly in the browser, like years before, that it didn't really need WASI because it's just a browser app. Usually those things aren't doing all this system low-level stuff. But now that we're doing cloud apps on a server, we actually need the app to do things like talk to the file system, talk to the network or whatever. So you're saying that means we're always using WASI when we're running these things, or we're trying to use the WASI standard as it becomes a standard or something, yeah.
Yes, like right now, if you want to do networking and stuff, and especially like moderately advanced networking with Wasm, then you pretty much have to go with something proprietary and hack something together. And companies are doing that, don't get me wrong. But I think the idea or the end goal is like a lot of this stuff will just be exposed through WASI. Okay, this command that I've put on the screen now has wrapped, unfortunately, over the first line. But look, it's just a Docker run. We're going to get rid of the container at the end with the RM. We're giving it a name. Then the runtime, we're saying here, use Wasm Edge. Okay, so it's using container D. In fact, let me just highlight this here. So we're saying for the runtime, we're going to go container D, but behind container D, we want container D to use Wasm Edge, which is one of many low-level, and when I say low-level, I'm talking here, we've got container D as a high-level runtime, and then something like run C as a low-level runtime. Wasm Edge or Wasm Time and things like that are very much in the space of run C, where they sit below container D. But the one that works at the moment with Docker Desktop is the Wasm Edge runtime. We've got the platform flag again here, Brett, and then it's basically just that local image, which I did change to be this. This is us using our typical Docker tools to run a WebAssembly app. Just honestly, Brett, a really quick recap here. We've built a hello car. You're better at me than that. So we've built a hello car app in WebAssembly, in Rust. We've compiled it to WebAssembly. We've packaged that inside of a Docker container or an OCI container, and we're now about to run that app. And if this works, please demo gods, we will get something fabulous. Hello car.
So in the background, you told the Docker command line this command. Then it passed information to the Docker engine. That's all normal. That's what we normally do. That's running in a Linux VM on your Mac. Then that tells container D to start an application image. And it says, hey, but this time, don't start run C. Start Wasm Edge. And you're going to, instead of a Linux, you said you're on Intel, so it would be a Linux AMD 64 image, which would be the default that you would normally run. It's saying instead containerd Wasm Edge runtime, you're going to run a WASI Wasm platform, which is actually architecture agnostic, which I think is fascinating. Like you could run that same image on Windows with a Windows Wasm Edge in theory. And then
100%.
the app is just running like normal.
Yeah, absolutely. 100%. And if anybody's head's like mine is going with all of that, totally normal, because there is a lot going on behind the scenes here, especially if you're new to it. But don't let that put you off, because there's a whole new conversation, Brett, that this is running inside of the Wasm Edge runtime, which is like a sandbox environment with a stack-based virtual machine executing the code. But it's also dressed up in kernel namespaces and C groups and things like that, but not quite a full container, but a bunch of container constructs there as well. So in some respects, we're getting like double security here, 2 for the price of 1 almost. So lots of stuff going on.
Yeah.
But at the end of the day, our existing tools and tool sets that we're familiar with, that we know usually we love, and we're rocking with WebAssembly with them.
Yeah, so we've gained a smaller image with a single file in it without needing a whole bunch of additional tooling or dependencies. Of course, with Rust, that's normally what Rust people are used to, but maybe if you're using something like Node.js or another Python or another language that supports Wasm, you simplified that workflow. And then you're talking about this additional, this is more of a Wasm thing specifically, right? That's additional security layer of Wasm already being sandboxed because it came from the world of WebAssembly where everything in a browser is sandboxed, so we're used to that model in browser world. And now you're seeing it as a regular image. It only has a slightly different metadata file where it just slightly says the OS and architecture are WASI and Wasm, and not a Linux / ARM 64 or AMD 64 like we're used to. And other than that, not a lot has changed about this. I'm still using the same tooling. I'm still running it the same way with Docker. Presumably when we push this to a Kubernetes cluster or a Docker engine server, like it's just running the same way as before. We might not even be able to tell from like an operator perspective. We're not really maybe aware of what's really going on here that's different unless we really dig into let's assume it's running on a Linux system. I guess I would see the Wasm Edge binaries actually running on the host OS, right? So instead of run C, it would be this other one. So we're just really trading one little runtime for another little runtime. Not a huge lift. So I like it. Let's do it.
Yeah. And do you know what? One last thing, and it hasn't wrapped on the screen. It's perfect size. We can see that it's about 500K. Now, look, I get it that it's just a Hello World app, but I have compared this to a similar one that I've got in a Docker Hub repo that was built with a small container image. And that one was, if I remember right, it was about 4.9 meg. So this one is like 0.5 meg. So for the equivalent, we are still significantly smaller here.
Yeah, this is floppy size, man. We could put this on a 3.5-inch floppy.
Who even remembers what they are? Bet you a bunch of people on the call don't even know. What are you talking about? But absolutely, yeah.
Well, thank you so much, Nigel, for hanging out with me. And we can find you on the web down there at Nigel Poulton on Twitter, nigelpoulton.com. You can find me, brettfisher.com, at brettfisher. We're basically all over the internet. Thanks, Nigel.
No, mate, absolute pleasure. Thanks for having me.
We'll see you all soon.
Welcome to this presentation about WebAssembly, also known as Wasm. It's an exciting new technology. We will be exploring how it works and how it fits in the Docker ecosystem. I'm joined today with my co-worker, Axel Alexandrov. He's one of the members of Wasm Labs, which is a team at VMware's office of the CTO of developers building tools for other developers working on WebAssembly. You can check it out at wasmlabs.dev. Everything that we do is open source and we build it in the open. So what is WebAssembly? WebAssembly at its core is a binary format. It's a way of defining executables, and it's also an open standard. So you can compile programs to WebAssembly and run them on a variety of environments. WebAssembly started in the browser side, and nowadays all of the major browser platforms from Chrome to Safari support WebAssembly. So what does that mean? What that means is you can take a program written in a language like C or C++, or even more modern or more recent languages like Rust and Go, and you can compile that source code into a WebAssembly binary. Then you can take that WebAssembly binary and run it inside the browser. Typically, the WebAssembly runtime that runs the binary is co-located with the JavaScript engine. So if you're using Chrome, the WebAssembly runtime will be part of the V8 JavaScript engine. By default, the WebAssembly runtime is completely sandboxed and cannot access the outside world. The only way to communicate with the outside world is through bindings. In this case, bindings to the JavaScript engine, which in turn allows WebAssembly to access indirectly HTML and CSS. From that perspective, you can think, even if the comparison is not entirely accurate, you can think of WebAssembly as Java bytecodes and the WebAssembly runtime as the JVM. So what can you do with WebAssembly? With WebAssembly in the browser, you can run video games, you can run like design applications like Adobe Photoshop or Figma, which is now part of Adobe, or Google Earth used to be like a completely desktop application that now you can access just by going through a URL. So it's having like a high performance environment for running programs that traditionally used to be desktop-like in the browser. So that's very interesting, but you're probably wondering why I'm talking about WebAssembly in a Docker Community Day, in which Docker for the most part is technology that is for servers or is for developing on the command line, is not for developing browser applications. All goes back to this tweet by Solomon Hykes, which was one of the co-creators of Docker, that if WebAssembly plus an associated standard called the WebAssembly System Interface had existed in 2008, he wouldn't have used Docker. And that's how important this technology is and why that technology is the future of computing. So those are big words. By the way, I agree with Solomon. Let's explore it a bit. What does that mean, right? So what that means is the first part of the diagram that I showed before is exactly the same one. You still get the source code for the program that you want to run in WebAssembly. You compile to the WebAssembly binary, and it still runs in a Wasm runtime. But that Wasm runtime, since you cannot rely on having a JavaScript engine, actually interacts with the outside world or interacts with the operating system through a different set of interfaces. One of them is the WebAssembly System Interface that I was mentioning earlier, but there are also other interfaces for dealing with networking, dealing with database access, with neural networks, and so forth. So why would you want to run an application in WebAssembly on the server side versus wanting to run that same application natively? So WebAssembly provides a bunch of features that make it a very interesting choice for running it on the server side, not just in the browser. The first one is a completely open standard that has been widely adopted. So companies as varied as Docker and VMware, Intel, ARM, Google, Microsoft are backing this standard. It really is industry-wide. It's tremendously portable. It runs on all kinds of CPUs from x86 to RISC-V. Most operating systems, mainstream, POSIX, non-POSIX, real-time. It's also is very fast, and for many scenarios is as fast as native applications or close enough. It's also very efficient. It requires like a minimal, it has minimal memory requirements and CPU requirements. It can run in devices for IoT or devices that have microcontrollers. Because of the browser heritage, it has a lot of security-related capabilities. Is sandboxed by default. You cannot do anything unless you give it specific access. Just like when you access the camera in the browser, you need to give permission to that particular web page to access the camera. You have to give specific permissions, specific capabilities to the applications running on the server side to access the file system or access the network. And finally, is polyglot supports for a lot of different languages. the actual support varies, but it's getting there, right? It supports most modern tool chains. You can think of WebAssembly as both the evolution of traditional server environments or a new take that we're going to talk a little bit later. So the first take, you can think of WebAssembly as one step going from physical hardware, which is how we used to do things back in the 90s, to having virtual machines or cloud, which is basically virtual machines running on somebody else's data center, allows you to extract that physical hardware and have the unit of deployment being a virtual machine. So you take like an operating system, you take the applications, and you put that into a VM or a cloud image and run it. Then when Docker came along and popularized containers, you could run containers. You didn't have to worry about the operating system. You could just worry about the libraries and your application, and you could ship your application and all of the dependencies in a container that make it a lot more portable and make it much easier to automate or deploy. So each one of these have different levels of isolation, has different level of footprints. Like virtual machines, you typically are in the range of gigabytes of in terms of size. Containers tend to be hundreds of megabytes, low gigabytes. With WebAssembly, you can get into tens of megabytes or directly on megabytes. So in terms of size, it's kind of like the next logical step. And also in terms of isolation and kind of like the level of abstraction that you're doing is also like a step further. Has much more stronger security boundaries than containers, which use the Linux kernel processes. And in terms of abstraction, you only care about the program, you only care about the libraries, you don't care about the rest of the operating system, because there is no such concept of the operating system. So this is one way, and this is what you may have heard, that WebAssembly is going to replace containers, or is what comes after containers. There is a different take, which is to take a look at WebAssembly as an alternative to containers. So when you're using Docker, by default, you have this tooling that allows you to build containers, to run containers, that makes it easy for you to build and share these containers with other developers or other users. But you're sharing a specific type of containers, which is a Linux container, right? So when you're executing with Docker engine and containerd, it will have a shim that will call the right kind of backend to run the right process. So in traditional Linux environment, you will just start a process that has a series of restrictions, run C groups and what you can do, and that's, you're starting like a container process. You could keep all the tooling, you could keep all the user experience of Docker and replace those Linux containers with a WebAssembly module or a WebAssembly container. In that case, instead of using run C to start a container process, you will be using a WebAssembly runtime. In this case, for Docker Desktop, you can use Wasm Edge to start a Wasm module. From the perspective of the user, very little changes. And from the perspective of the backend, now you have access to this new backend technology that allows you to leverage all the characteristics that I mentioned earlier. And we'll see that in the demo. Talk a little bit about Wasm Edge. Wasm Edge is one of many different WebAssembly runtimes that are in the market right now. We chose Wasm Edge because it's open source and is part of the CNCF. It's quite popular. It supports a lot of different CPU architectures, from x86 to ARM to RISC-V, as well as a lot of different operating systems, all the mainstream ones like Linux, Windows, and macOS, but also a lot of more non-Linux based like real-time operating systems and others. It has been optimized for cloud native and applications running in the edge, There's a lot of other things that other more minimalistic runtimes may be more suited for. We believe that this is like a good balance. And then finally, it's extensible. They have been adding very quickly support for different technologies. Some of them are standardized already by the Bytecode Alliance, which is one of the foundations that are working on WebAssembly. And some of those are being standardized. Some of them Wasm Edge is building on their own with an eye to when they get standardized, they will be contributing back or adapting to it. But if you want to use today, neural networks, you want to use AI inference, you can do so very efficiently with Wasm Edge. There's a lot of networking capabilities. We'll be using some of those during the demo, and as well as integrated with the rest of the container ecosystem, including Kubernetes and Docker. Docker partnered with Wasm Edge for this initial version of Docker Desktop with support for WebAssembly, and you can go and check it out on GitHub. We are going to be using PHP for the demo of how to put all these different pieces together. And in contrast from when you compile like a file from C++ into a WebAssembly binary, with PHP, you do something slightly different. You don't compile the PHP application code directly to WebAssembly. There is not such a compiler or transpiler. What you do instead is you compile, or what we have done to be more exact, what we have done is compile the PHP interpreter, which is written in C, into a WebAssembly binary, and then that WebAssembly binary can read or can bundle that PHP file, then being executed on a WebAssembly runtime. Wasm will go over this in the demo. As part of the work that we did in Wasm Labs, we ported the PHP runtime to WebAssembly. There were already like ports of WebAssembly to the browser using a toolchain called Scriptem. This toolchain leverages JavaScript functionality that you can find in the browser to emulate or provide networking and provide a lot of the things like a POSIX environment is expected from a POSIX environment. The WebAssembly system interface port that we are contributing back, it is focused on server environments. For that, we reuse or use tooling like Wasm to emulate or stub out functionality that has to do with POSIX, like signals and getting process IDs and so forth, as well as remove functionality that it's either not needed. There is now the concept, for example, of processes in WebAssembly being able to execute other processes, or that were not supported, right? Some of them are there, and for the most part, file system access is there, but things like changing permissions on that will basically not work or be ignored. And with that, even with all these restrictions, you can run like very complex, very sophisticated applications like WordPress, and we'll be seeing that during the demo. So without any more delay, I will leave you now with Wasm, which will put all these different things that we saw in this first part of the presentation in action. Thank you.
Thank you, Daniel, for the great introduction. Now, let's get our hands dirty with a few hands-on examples. We'll see what it takes to build the WebAssembly module, to put it into an OCI image, and run it on Docker Desktop, along the line comparing it with the same running as a native binary. For the sake of this demonstration, we'll be using a PHP Wasm binary, which we built for another project. Then we'll compare what a running container behaves like in terms of WebAssembly container and a normal container. And in the end, we'll stress on the portability of WebAssembly and why WebAssembly plus Docker is much more than traditional containers. Building and running a WebAssembly container is not that hard. We start by using the normal PHP code source base, which is written in C. We use the WASI SDK package, which combines a compiler with WASI libc, a runtime library, compliant to glibc, and then we can get a php.wasm binary compiled to WebAssembly. Wrapping it up in an OCI image is very simple. The Docker files always start from scratch, and you just copy your Wasm image. And there you go. You have a container image, which you can use with Docker Desktop plus Wasm to run it just as you would any other normal container. Let's see what lies behind the step of building. Now, this is our simple build script. The important thing is that you need to set your compiler, your linker, and everything else based on what you get from WASI SDK. And then you will run your normal configure or CMake or any other build system script almost as close as to what you are used to. So let's just do that. This is a normal autoconf script combined with make. Of course, we're not going to wait for it, so let's skip to the end. Now, we've got a few binaries here, but for the sake of this demonstration, we'll use only the ahead of time compiled binary without going into much detail. It will give us the best performance. What does it take to build this into a Docker image? I've got two Docker files here. One will just build a container with the simple PHP CLI command, and another will build a container with some built-in examples which get served on a certain port. The commands to run these Docker files are also pretty simple. Here is the script with them. And now let's run the script and get those images. Pretty fast, but that's all when the only thing you have to do is just copy. Let's take a look at those images. Here they are, PHP Wasm, and a very small size. For the sake of our next demonstration, we'll be using the same index.php file and running it with a native PHP binary and a WebAssembly-based binary and comparing the results. So let's take a look at the index.php file first. We'll just print the PHP version, the platform on which the interpreter is running. Then we'll get a list of the environment variables available to the script. Then we'll just print the current date and time to say hello and print the contents of the root folder, which is also available for access to the script. Now, let's compare running this natively versus running this with WebAssembly. Here is our plan. We start with the index.php file that we saw. We'll first interpret the index.php file natively, running on my machine. Then we'll interpret it using the PHP WebAssembly module running inside of a Wasm runtime, in our case, Wasm Edge. Let's run the native app and see what happens. And as a result, we get the version, we get our platform, Linux something, we get a huge list of environment variables available to the script. This could be some kind of a security implication, because God knows what's in that script. Then we also get a list of all the contents of the root folder on my machine. Let's compare to the same thing, but in Wasm Edge. Take a look at this. We have the same version. The platform, however, is WASI. That's short of WebAssembly system interface. We don't have access to any environment variables. The time is correct. And we have absolutely no access to get the contents of the root folder. Because with WebAssembly, you can only access the files and folders which are pre-opened whenever you run the WebAssembly binary. So in our case, there will be a folder called docroot, and it will contain whatever is in this folder on the host machine. And that's the only thing that the file system inside of the WebAssembly program is capable of accessing. So that's why we get capabilities insufficient and absolutely no access here. The same goes with environment variables. You can set additional environment variables whenever you run the WebAssembly module, and you will have access to them. But in our case, there is nothing. What actually happened is that by just compiling PHP to WebAssembly and running the same index.php script there, we get automatic security. Now let's move on and see how that behaves when you use Docker. On the top, we'll see what a traditional container looks like running the native binary in a PHP 7.4.32 image base. And at the bottom, we'll see what our PHP Wasm image base produces in terms of a container. Running the native image in a Docker container looks like this. We see something similar, same version of PHP. We see again the Linux kernel. Of course, we see fewer environment variables, in this case 14, because this is all running in a container context and is more secure. And the contents of the root folder is also limited, but still we do have access to a lot of stuff. Let's take a look at what running this with WebAssembly in Docker looks like. Of course, we'll need to provide a specific runtime and platform. This may change with time, but that's the way you do it now. Then, for the sake of mapping the doc.root folder, we use the well-known syntax from Docker. Here we still have improved security. First, there are only two environment variables inside for the sake of infrastructure, path and hostname. Then the contents of the running container is just the doc.root folder and an infrastructure etc and the PHP Wasm binary, and that's all. And now let's take a quick look at the differences we can see with a plain eye between traditional containers and containers based on WebAssembly. For the sake of this demonstration, what I'm going to do is I'm going to run the PHP server natively and with WebAssembly, exposing some port here and the doc.root, and again exposing another port here and doc.root, where again we will serve index.php. Now let's do that. We will be running daemon containers, which will stay in the background, and this will allow us to see statistics, behaviors, memory, etc. Here we see that we are serving the index.php file all right, and we are listening on 8081. And now let's run the WebAssembly version of this thing. And we're listening on 8082, again serving index.php. Now, let's see what those running containers will show us in terms of stats, numbers, etc. Running the Docker stats doesn't show much yet, because for WebAssembly, not everything is still implemented, but we can use the interface to monitor control groups if you want to get a little bit more information about what's going on. Now, something of interest here is that traditional Docker containers get their own control group, so you'll see them here, but WebAssembly-based Docker containers are all within the pod runtime Docker control group. So if you're monitoring what your container consumes in terms of memory and resources, you could be watching what goes on here when you spin up more and more WebAssembly-based containers. And finally, let's take a look at the different images. Normal PHP images take a lot of space, and that's expected because in those images, you get an image of the operating system with lots of runtimes, libraries, etc. With WebAssembly, you only need the WebAssembly binary. The runtime is embedded into Docker Desktop, and you just use it as is. And we have summarized this difference here. Traditional images get you lots of stuff which you may not necessarily need. WebAssembly-based images get you just what you need in order to run that application. For the last part of our demonstration, we'll talk about WebAssembly portability. Why is that important? Docker gives us portability in many ways. You can build your machine here and ship it somewhere else. But that's with a catch. It will work only if the recipient has the same architecture. Now, of course, there are cases where the recipient may run a virtual machine with emulation and stuff and still be able to run your Docker image. But let's face it, we often have to build different versions of the same image to be able to support different architectures. With WebAssembly, that's not the case. You build once and you run it everywhere, and that's a promise. Now, let me give you a short demonstration of how that works using the PHP interpreter, which we already have, and running WordPress in it, and running it on different platforms. We'll run it on Wasm Edge locally on my machine. We'll run it on Docker using the Wasm Edge runtime, which we already demonstrated. We'll run it inside of Apache using ModWasm, which embeds a WebAssembly runtime and can interpret the WebAssembly modules freely. And then we'll show how WordPress works in a browser, again leveraging our PHP interpreter compiled to WebAssembly. Let's go. So first, we are running Wasm Edge locally. And you can see, here goes WordPress. Now, we're going to use the same PHP Wasm binary and run it inside a Docker container. And then we'll move on to do this with Apache, as I said, and a browser. So here we are running WordPress in Docker. And now let's run this in Apache using ModWasm. Of course, I don't have Apache installed locally, so I'm going to use a traditional Docker container to run it, which takes a little bit more time just to load the container in Apache inside. But in the end, here we are running WordPress interpreted by the PHP WebAssembly module, loaded by WebAssembly runtime inside the mod Wasm extension to Apache HTTPD. As a final step, let's run WordPress in a browser. And here it is, again, interpreted by a PHP WebAssembly module, but this time running inside of your browser. So, as a recap, we showed what it takes to build a WebAssembly image and put it into a Docker container, how easy it is to run it. What are the little differences that you can see when you run a traditional container versus a WebAssembly-based container in Docker Desktop? And then what's the big deal about WebAssembly and why it seems to be the true promise of portability? If you want to run any of these examples, Daniel will provide you with a link which you can check out after the demonstration.
That was a great demo by Asen that hopefully let you visualize some of the concepts that we described early on. Thank you for watching. Please follow us on Twitter or go check out and try by yourself at the URL at the wasmlabs.dev/docker. And looking forward to getting your feedback and maybe getting involved with the project. Thank you.
Hi, I'm Ralph Squillace. I'm a principal product manager at Azure Core Upstream. That's at Microsoft, and we're the Deus Labs team, if you're familiar with that. And we've been working with WebAssembly for many years now. It seems like probably just one, but it's really more like three or 4 years. And I've got about 10 minutes to talk about WebAssembly, Docker, Containerd, and then Kubernetes before I can get to a bunch of demos. And then we can have a whole bunch of questions, or at least that's the theory about how this is going to work. Let's see what we can do. So the agenda is pretty straightforward, right? Why the heck do we want to use this stuff? How does Docker Desktop do the WebAssembly magic as opposed to the container magic? And how does that WebAssembly magic connect to Kubernetes? Now, if we do that, then we're going to run into some demos, which is where I get to show you the stuff, and that's the fun part usually. So why the heck do we want WebAssembly, right? Wasm is WebAssembly. And the main point here is that we want features. That's it. Nothing but features. The features are mainly cold start speed, pure speed. You can optimize the startup here down to nanoseconds, but out of the box with these models and runtimes, you get very single-digit microsecond cold starts. That's fantastic and almost impossible to achieve with container architecture, right? Mainly not due to any fault, but mainly due to the fact that there's a whole kernel, a whole operating system to start. The size is very, very small because you're not bringing a whole operating system. You're bringing really one function, one code path. It's a binary. And that makes a huge difference for not just speed, but also things like transport, storage, the whole ball of wax. There's a default security ease factor at play here as well. WebAssembly has a sandbox, and that sandbox is by default full deny access to outside functionality. That's the opposite approach to default security that the container ecosystem has, because in containers, you share the kernel of the operating system that you're running on. And we spent a whole bunch of time with distributions making sure that that's controllable from the outside. WebAssembly actually gives you that stance from the beginning. The host controls everything, and you get to opt in to any functionality, no matter how dialed in and controlled it might be, and that is a wonderful stance to start from. And in the world we exist in, and the world that's coming, that's going to be more and more critically important. Finally, there's portability, radical portability in 4 dimensions. I usually talk about them this way. You have language and runtime and tooling portability. You have the ability to ignore operating systems for the most part, including use operating systems don't have containers on them, real-time operating systems, and so forth.
You have architecture agnosticity, so you can not really worry about what architecture your node is, and that has cost effects, but it also has locational effects. Right? You can run on little teeny chips somewhere in the middle of nowhere, and that's really useful. And then finally, those locational effects, in a lot of ways, help you bring compute to the data. There's now just so much more data than ever existed, and that's going to continue to increase. So you need to make the compute work with the data, not make the data work with the compute. And so those are the main feature sets that we're looking for when we talk about WebAssembly. But we also need to clarify that by talking about when you don't want it, right? So if you don't need super fast cold starts because you have a big long-running process, right, then WebAssembly on that feature, in terms of that feature, doesn't make sense. It doesn't make sense for you. Or if you live in a huge public hyperscale cloud like Azure or like DigitalOcean or Alibaba or something like that, right? You don't need anything but containers and Kubernetes there. It works great. Enjoy yourself. Have a great time, because those teams and those engineers are helping all of the feature set that you really want, the security and the scalability and all that stuff. They do that work along with you, which is fantastic. Or if you need to Xcopy something and have an entire operating system with you, right, in order to have something run, that's what containers do. And WebAssembly doesn't do that. It's a binary right now. Yes, in the future, you can probably have a WebAssembly that has all of an operating system in it, but then you're going to end up losing a lot of what WebAssembly is really fantastic about. You might be able to do it in 3 or 4 years, but right now, no. And the same thing goes if you have long-running, heavy scheduled processes, scheduling process, orchestration processes, like web servers or scale-out databases or something like this. Those kinds of things don't work well in WebAssembly right now, and for the very same reason. You don't have threads. You only have 32 bits of memory space, so that's 4 gigs. Here's the obligatory quote: nobody should ever need more than 4 gigs, really. I hope to be quoted about that in the future, 10 years from now. So there are good reasons why you don't want to use it. So when do you want to use it? Again? Okay, to get even simpler, when you want to do something with native code that native code or containers don't do, a lot of that has to do with the portability. It has to do with the speed and stuff like, or like they don't do it at all. Like you can't run containers in certain environments, for example. And if you need to run there, it's important. Your work is mostly new, maybe, or it's absolutely worth it to obtain some of these features to do something brand new that is of such value that you will recompile and modify the code you already have. If you have fast-firing functions already, then WebAssembly just makes those amazingly better and more portable. That just full stop true, and so that's a great scenario there. Or if you already have expertise with WebAssembly tools, if you're running with WebAssembly in CDNs or in web browsers and so forth, maybe you can just take advantage of those same abilities and feature sets somewhere else. So that's really right now, these are the sweet spots for the technology. Now, how does Docker Desktop do all this magic? Well, it uses Containerd and a Containerd shim. And now, if you don't know a lot about Containerd, there's a couple of links here. You can look it up. It's well documented. Containerd is a CNCF project. And Docker Desktop's Wasm feature hooks into this and uses a Containerd shim directly to enable WebAssembly alongside containers. So if you want to look at the Docker Desktop command that runs it, you can do it very straightforwardly. Docker container run, and then use the runtime path and specify the shim and, of course, the workload. And it'll just launch the shim that knows how to run WebAssembly as opposed to the shim that is supposed to do the process that, knows how to run containers. So that's fantastic. But let's get to some history too, because if some people are aware of what's going on in the ecosystem and others are not. So the shim that Docker Desktops uses is called runwazi, but it's different from, and it uses the code from the runwazi that my team built. But my team built originally the shim with the Wasm time runtime. And we did that because we were thinking about Kubernetes and we wanted to enable pod semantics like containers, networking, and storage. I wanted to inherit that from the standard kubelet. We wanted to be able to ignore completely the node architecture, and we wanted the Wasm feature set, all the size, density, faster deploys, and all that stuff. Now, Docker and Second State were also in the ecosystem thinking about how they wanted to run. And they were looking at runwasi as a containerd shim example. And so they forked runwasi, and second state put in the Wasm Edge runtime, and then added OCI lifecycle hooks together so that Docker Desktop could do the beta, what was the alpha, the tech preview, and now just released the beta feature for WebAssembly, the one that we just talked about. So if you're thinking about that, you're thinking, okay, wait, fork is a 4-letter word with an F in front of it. Is that bad? And the answer is no. This is a healthy example of forking, because runwasi had the core idea and it had different features, and we'll talk about that. What you should see coming, part of which you're already seeing coming, runwasi from Deis Labs is now part of the containerd project at the CNCF. So that's the kind of formal runwasi project there that is a containerd shim that runs WebAssembly. Now, second state and Docker are working with us to bring in the composable runtimes. You should be able to just use runwasi, but select the runtime you want. And Docker and second state wanted to use and enable features of Wasm Edge that Wasm Time doesn't have. And there are other features like Whammer has features, and Wasm 3 has features, and other Was0 has features, and so forth, that you might want to use. And so you should be able to specify one shim and a runtime and get the feature set that you want to work with in Docker Desktop and in Kubernetes. So we're doing that work up there. And then item 3, Microsoft, Docker, second state, and other contributors, I'm thinking about the Yuki maintainers, are thinking about how to bring in the remainder of the OCI feature specification. And that'll end up including things like OCI artifacts, which Docker Hub just announced that it would have support for. And finally, Docker is thinking about how to enable the selection of shims in Docker Desktop. So there might be a default shim like runwasi that is useful generically, but there may be custom shims you might want to use, and Docker Desktop should enable you to do that. In the end, over the next 3 to 6 months, depending on our day jobs, you should be able to build, test, run WebAssembly containers in Docker Desktop and push to Docker Hub, for example, any OCI registry, and then deploy directly to Kubernetes, the very same app, without even thinking about the fact that it's WebAssembly per se. That would be the objective. And in fact, all of these streams are coming together. So how does that connect with Kubernetes? Because the original objective was, in fact, to connect with Kubernetes here. And it uses the containerd shims. And containerd is the hinge between the kubelet on the node and the process model, whether it's run C or whether it's a WebAssembly engine of any sort. So let's see how this works. We're going to use K3ds, and we're going to use the containerd runwasi shim. So this doesn't work running in Docker Desktop yet, but it will hopefully soon. And it uses 2 different application models that are based on Wasm Time instead of Wasm Edge or another runtime. So this is an example of the different functionality and dependencies of the runtimes. So we're also going to use K3ds because it demonstrates that you can run this on a single node very, very easily, as well as in hyperscale. But we're going to start with a single node. Now I'm going to set up the containerd demo in Kubernetes, right, using K3ds, right, from Rancher and SUSE. And this is just Kubernetes in a container. And while it sets up, the important part is to realize that this is the same shim that is in containerd project. And when we get the chance to merge all the runtimes, it'll be the shim that you can use with almost any Kubernetes distribution, unless you want to do something really, really custom. It doesn't matter what runtime. So given that's the case, we now have a cluster. By the way, this is mostly in real time here. So first thing we need to do is inform Kubernetes that the shims and the binaries that the shims have are on the cluster. And so we do that by telling it about the runtime class. We can then actually lay down a workload. In this case, the manifest has 5 versions of a slight hello world application, 5 versions of Spin. Spin is from Fermion. And we'll talk about that a little later. But you notice they come up in like 4 seconds, like they're already there. And yet what we're doing is we're waiting for, ironically, a real container, the Trafic container, to come in so that we can have ingress functionality, right? And so we're going to sit here and wait for that, a real container, while their actual WebAssembly workloads are already spun up. We got it. So we start hitting it. And right here, I've sped it up a little bit, only because nobody wants to see me fail 37 times until I succeed. That means the container, the ingress, they're all registered, they're working, and so forth. And so I can go ahead and clear the thing and show you that hello world is there for slight and hello world is there for spin, right? I got to type it correctly, but it's there. Okay, so I'm going to go ahead and tear everything down again. And you'll have this video like just to see like the whole process of bringing it up and tearing it back down, and it should work exactly the same way no matter where you are. That's all well and good, but while that happens, I want to point out that this is a single node cluster. It's actually multiple nodes, but it's a single container cluster and can run anywhere, a phone, a car, an elevator, whatever you want. It's a very, very different environment than container clusters are. And now we're going to try it with Azure Kubernetes Service. But before we do that, I just want to chat very briefly about performance. Now, these are spin functions from Fermyon that we used here, and I want to show you exactly how fast this is. These are just hello worlds. They're local because it's K3ds, right? But you can see that we're averaging 5 microseconds per request here, and the fastest are down to 2 microseconds. This is extremely fast, and it's got out-of-the-box performance, unoptimized on the laptop that I'm recording this demo on. The slight functions are in fact slightly slower, but there's a reason. We are using the file system to simulate a key value store. And even in this case, we are actually running at about 11 microseconds per request, just over 1 millisecond. But we're using extra functionality, which is why there's a speed difference there. This is incredible performance. So, can we use the same application set in Azure Kubernetes WASI Node Pool Preview? And the answer, of course, is yes. So let's have a look. So here we've migrated from using K3ds to using AKS. And you can see that here we've set up 2 node pools, WASI Pool 1, which is an AMD 64 architecture, and WASI Pool 2, which is an ARM 64 architecture. And ARM nodes are much less expensive in general. So one of the effects of having two different architectures with a regular container voting app, you can see that if we actually get scheduled accidentally to the ARM node, we bonk. I can't find the image. It's not made in multi-architecture. I now have to go back and do a whole bunch of work. I either modify and add node selectors to my Helm chart, or I have to actually do multi-architecture builds and push 2 different images and so forth. So what if we do if we actually deploy the same application that we did on K3ds, right? If we do that, very quickly you can see that they're just evenly distributed throughout the nodes. It doesn't matter to the application because it's WebAssembly. And so in this case, the container sort of node relationship in terms of architecture just goes away. I can prove that here by going and finding WASI Pool 1, which is the node pool that's AMD 64, and just deleting it out from underneath the cluster. Now, what happens if I do this? Let's watch. I haven't sped this part up at all. We're looking for the termination. There they are. The nodes are going poof, and Kubernetes has already redistributed the WebAssembly apps onto the ARM. You can see it's WASI Pool 2 all the way down the nodes, and the containers still failing, and WebAssemblies have been completely migrated all to ARM, which is less expensive. And you didn't do anything at all. But let's have a little more fun, shall we? Raina built a Fibonacci tree app on his YouTube channel using Docker Desktop in its environment, and walked through for about 25 minutes how it worked. Built a Fermyon spin function that does Fibonacci trees, and pushed it to Fermyon's cloud, and also pushed it to AKS. And what I wanted to do was do the same thing we did with the AKS thing. I wanted to take Rainier's application and deploy it in Fermyon Cloud and AKS, but deploy it across multiple nodes. So let's do that. So what I wanted to do with Rainier's module that he had just built in that YouTube video, I wanted to deploy it in a different way in AKS than he did. So let's go look at his Docker file, right? You can see it there. It's a scratch file with the spin module and the spin toml in it, and that's all the container is, and he pushed it to Docker Hub. But for my AKS cluster, what I'm going to do is create the same one I did last time. I'm going to use both AMD and ARM nodes in a mixed configuration, just to demonstrate that it's not just my application. I can take Rainier's application, just like it's a container because it's a module, it's shoved into Docker Hub, and I can deploy it here on AKS, and I actually don't have to care what nodes I have at all. They could be big nodes, they could be small nodes, they could be ARM. If other architectures are coming, such as RISC-V and so forth, they should just work and so on. So you can see them lay out right there. And just to make sure we know the application is running, we go ahead and look for the service IP. Oh, and there it came really fast. So let's grab it. And we will get our hopes up for instant satisfaction here. Usually it takes a little bit to kick in, but no, we get instant satisfaction. Okay, great. Now what I wanted to do was compare this actually to the Fermyon app. This is the same exact app that Rainier built and deployed in Fermyon. And so we can look at that and we can grab some of the depth query string and modify it, and we get a kind of a richer, bushier tree. And we should be able to grab that query string right there and drop it into, there we go, into Kubernetes, and we get the bigger, healthier tree as well. And of course, now we'll have a little fun. Go ahead and kick it up a notch. This is a fractal, and we hit the resource boundary for Fermyon. Now that's by design, that's not a mistake. I've got the free tiers going on there, so I could obviously buy more resources. But with Kubernetes, I've got, you know, as much resources as the nodes will chew, so we can go to a even bushier tree than we could. So having done that, the thing that I want to point out is that you can see that 3 ARM nodes are deployed in 2 AMD nodes. And it just doesn't care. We could torch the nodes like we did with the other demo easily, and it would just redeploy. So another thing I want you to see is just how small the container with the modules is, just like what we're going to show you now. So let's start by looking at our cluster. We have a Wasm cluster. And we go and look at the pods. And this service has an order service, a receipt generation service, and they're all clusters along with virtual customers. And what they're doing is creating receipts from the virtual customer orders. And these are the receipts in JSON being written to Azure storage blobs. So if we flip over to Azure storage blobs, again, this is just a multi-service container application. You can see that we're processing a whole bunch of JSON formatted receipts. Okay, so that's pretty straightforward. What I want to do now is go ahead and get the deployments. You can see the 3 services. And we're going to delete the container-based receipt generation service and go ahead and we'll actually spell it correctly. And we're going to go ahead and add the same service back, but the implementation here is WebAssembly. And in fact, this wasn't used with Docker Desktop, but you could have built this service with Docker Desktop, which is entirely the point. So here it's being created, and once it is, we can now go and refresh the application and run and refresh on the blobs, and you can see that we're pumping out more receipts, which is fantastic. But here's the most important part. If we go and let's look at the images, you can see that the WebAssembly module is actually only 2.9 megabytes, whereas the container it replaced is 210. That's something else. So that's it for the demo fun that we have. So that's it for the demo fun that we have. And I hope they all showed you various aspects of benefits and features that you could obtain using Docker Desktop and Kubernetes with WebAssembly, no matter how you're doing it. And you can see some of the future that we're going to, as we unify all of these things into one nice workflow. But I do want to call out a few things. I want to thank Docker for the desktop with Wasm support, and to them and Second State for the Run WASI work that they did that will move upstream. I also want to call out and send some love to Rainier Stropik for his video tour. Go and have a watch. And if you're interested in everything, if we've done the job right, then do these things too when you have time. If you haven't, install and play with Docker Desktop and enable the Wasm support. Dork around with Fermion Spin and Spider Lightning from Deus Labs apps and build Scratch containers for them with Docker Desktop. Push them to Docker Hub and deploy to K3ds. Or create a cluster in Azure Kubernetes service and add a WASI node pool to deploy it there. But above all, have a blast doing these things because this is the fun part of technology. Thanks very much.
Okay, welcome everyone. Today we have a real special guest. This podcast is for the all hands of Docker, December 2022. And today we have Chris Miller from Washington. And why is he here? Because he's in the WashU, which is Washington University School of Medicine, and which is basically a team of bioinformatics developers, and they use Docker for their research for analyzing the genome sequence and data cancer of patients, and they also do many collaborations with other institutes, right? And as in the words of WashU's Jason Walker, this really helps to accelerate science and medicine globally. So this will be a very interesting and exciting episode. So welcome, Dr. Chris Miller. Please introduce yourself. Thank you so much.
Hi, it's great to be here. Yeah, I'm Chris Miller. I'm an associate professor here at Washington University, and I study cancer genomics and bioinformatics.
Nice. So I would like to start with the introduction. So what is bioinformatics? How can we define it?
So simply put, yeah, sure. Simply put, bioinformatics is just applying computer science techniques to biological questions. And in our case, we study human disease with a focus mostly on cancer. So by sequencing the DNA of people with these diseases, we can try to sift through and find the mutations that are in this people's DNA that cause their specific cancer. Increasingly now we're able to also pair those up with therapies that target their specific flavor of cancer. And so there's lots of exciting research around that, ranging from better detection of cancer early on, through things like simple blood draws to doing things like improved treatments, immunotherapies or cancer vaccines that weren't available, years ago.
Nice. So this is very useful and great. So first of all, thank you for what you do. And I'd like to ask a bit more about you, if that's okay for you. So I'd like to know more about you yourself. Did you start working in bioinformatics? Because it looks really challenging, not easy at all. Basically, it's a mix of different technologies and skills. So informatics and other many more, medicine. So how has been? Can you tell us more about your experience and your career? Because it's very interesting. Let's see. Thank you.
Sure. I started out as a biology major and started doing a little bit of computer science here and there. Ended up double majoring in undergraduate, and then went to graduate school for my PhD. And then I've been working on cancer genomics here at WashU for over a decade postgraduate school. That said, a PhD isn't necessary to get involved in this field. We've got a whole spectrum of people ranging from, hardcore programmers who optimize algorithms and such, and to people who are bench scientists who just, learned a little bit of code to be able to analyze their data. And really makes our team works well is that we have like that expertise across the whole spectrum of it, and we're able to bring those to bear on the problems that are important, like cancer.
Nice. Thank you. And now I'd like to ask you about some numbers, because I don't have an idea on these numbers. So I don't know how many patients are involved in this research. So can you give us more like numbers to have an idea of the size of this whole research institutes? Thank you.
Sure. I mean, that really depends on the study. I mean, we might be doing big projects where we analyze the genomes of tens of thousands of patients to try to understand general trends about how cancer forms. Doing that on the cloud and doing things at scale. And other times we're working on single patients, doing a workup of one person's genome to try to inform their treatment in real time, understand why their cancer relapsed, and whether we can have a better drug to treat it. And so that's the idea of personalized medicine. And we're trying to really make that a reality for every patient.
Nice, nice. Thank you. And in the introduction, I talked about other institute in which you collaborate with. So can you give us an idea which are those institutes that you collaborate with, and how do you collaborate with them? Thank you.
Sure. I mean, all of science is kind of fundamentally collaborative, and we benefit from being part of a huge community of universities across the not only the nation but the world. Working on similar goals. People designing algorithms and sharing them, and just contributing to that large pool of knowledge we need to figure out how cancer works. And that ranges from giant centers like the Broad Institute in Boston that sequences tens of or hundreds of thousands of genomes to small labs with only a couple of members that carve out a niche studying one particular gene or one small aspect of a disease. So all of them have a role to play, and by sharing our code and making it available, we're all working together toward a common goal.
Nice. Thank you so much, Dr. Miller. Okay, so now I would like to go a little bit more into the main topic of this interview. Why are you here? Because there is this event by Docker. So we would like to know if you can give more details on how Docker can help you in this daily work. And sometimes can be very stressful, very overloading. So which can you go, if you can, a bit more into details in how Docker is helping you, if it's helping you?
I mean, sure, there's a few different ways that Docker helps us. First of all, the workflows we use to analyze these cancer genomes aren't just straightforward single scripts. They're complex pipelines that rely on dozens of different tools. We have to line data to the human reference genome and sift through it. Where in those 3.2 billion base pairs is there a mutation that might be causing the cancer? And then we have to filter them and categorize them using different knowledge bases so we understand which ones are important in driving the cancer. And so this results in kind of big, hairy pipelines that rely on lots of different code repositories, developed in lots of different languages by different groups. And so Docker allows us to kind of modularize that, build complex pipelines that chain these all together with a minimum of having to wrangle installation and dependencies, and also allows them to be run on all the different architectures we use, which range from those big projects happening on the cloud to analyses I'm doing on my own laptop. I would also say that the field is evolving really rapidly. It's often the case that we want to swap in a brand new algorithm for one that we're already using, and having that kind of modular Dockerized workflows really allow us to make that happen rapidly, as opposed to having to rebuild things from scratch. And I think the final point I would say is that reproducibility is just absolutely essential in science. In order to trust the results from another group, I need to be able to replicate those. And so by locking down the environment and allowing others to reproduce that exactly, Docker helps us make those results reproducible to the rest of the community.
Perfect. These words are really warming my Docker captain heart. So it's very interesting and important to try to have, let's say, other kind of problems, maybe, and not also software problems which can add up on the existing problems. Nice, thank you. And now I would like to ask you a last question about maybe it's more focused for the developers, but I saw that there is a GitHub organization or account which is called genome/analysis workflows, right? There is this repository that you use. So can you tell us more? Can you tell us more about this repository? I see there is an MIT license. Can developers contribute to it so we can give a shout out to this project? Thank you.
Yeah, we make all of our core pipelines and code open source. We're big believers that, fundamentally the things that we're working on, this medical research is too important to live behind firewalls and be locked down. And we want as many smart people working on these problems as we can find. So we absolutely welcome contributions from the community, whether those are from seasoned bioinformatics developers or people just dipping their toes into it for the first time.
Nice. Thank you so much. So this is also why Docker is sponsoring this program. So we're happy for this. I hope that we can help and we can find more people collaborating on this project. We will leave link in the description. And yes, so thank you so much, Dr. Miller, for your interview. It has been really a great way for me to start the week. And yes, so thank you. And anything else that you would like to add for this, and then we can wrap up. Thank you so much for staying with us so far.
Yeah, no, just thanks for the folks who build the infrastructure and tools that we rely on. You're really making a difference to human health and disease, and that matters.
Nice. Thank you so much, of course, from the bottom of my heart for what you're doing daily. And I hope that we can collaborate more in the future, trying to give support to these great initiatives and projects. So thank you so much, Dr. Miller. And yeah, have a nice day, have a nice week. I don't know what's the time there. Here is 4 p.m. I'm almost at the end of my day. Probably you are about at the beginning. But yes, nice. So
yeah, it's 9 a.m. here, so we're just getting started.
Yeah, nice. Okay, perfect. Okay, so thank you so much. Have a nice day, and yeah, thank you so much, and see you next time. Okay, perfect. Bye everyone.
All right, take care.
Bye everyone. Thank you so much for staying with us. If you have any question, just leave a comment below, and we will reply. But we will leave the links to everything we talked about in the description, so no worries. Bye everyone. Bye.
Everyone, and welcome to this community update where we're going to be giving our famous community awards. My name is Alba Rosa and I am part of the developer relations team, and I'm joined here by my colleague Eva. Hi Eva.
Hi Alba. Yes, my name is Eva and I also work in the DevRel team. I'm very well. I'm really enjoying the event. What has been your favorite session so far, Alba?
Well, I think it's been really interesting, everything around Wasm. I think it's something that our community has been very excited about. They've been very glad to hear and very happy to hear the latest. And what about yours, Eva?
Oh, I'm always a fan of extensions. I loved the tutorials given by some of our captains. I loved seeing some of the cool extensions that the community has built. So I'm really looking forward to seeing more of that.
Right.
So Alba, I think our community is very eager to know about what's coming up because it's the most exciting talk for our community, right?
Well, I don't know if it's the most exciting talk, but at least the most exciting part of these community all hands for the active members of our community, because we're going to be delivering or giving first of all, as I mentioned before, the community updates, but right after that, the community awards. Eva, would you like to start with the community updates? Perhaps you want to talk about the captain's program?
Yes, for sure. So for those who don't know, all of you who are new to the community, we have a very exciting program. It's called the Docker Captains Program. And if you're wondering who these people are, well, they are experts in their field and they are Docker thought leaders. So that means they drive the conversation around Docker. They are out at conferences. Many of them have their YouTube channels. They are active on Twitter, and they are basically the ones to go to if you have question about Docker. And it's also very exciting because internally, Docker captains are very important members for us because they get to hear about the newest Docker features, and they get to tell us their feedback, and we just love Docker captains. So if you're interested to join the Docker captains program, follow the URL in this slide, and you can see the instructions there. When you make your application, please remember to include all the things that you have done for your local community. If you have any channels, include them there, and tell us why you want to become a Docker captain, because that's always super useful. But that's not the only program that we have. I know we have another very exciting program, and that's the Docker community leaders, which Alba will tell you more about.
Docker community leaders are local ambassadors, and they're people that are always willing to share and to gather their communities. We get a lot of questions of people asking, hey, do I really need to be an engineer, for instance, to be a community leader? Well, the answer is no. I mean, it's appreciated. It's something that, of course, adds on top of that. Since, for instance, we also have community leaders that write blog posts, technical documentation, and so on. But it's not a mandatory aspect. The mandatory aspect would be your commitment and your willingness to bring the community together. We also have the website there, so you just can take a look at that website, the Docker link you see over there, and where you can check the information, some benefits, and of course you can sign up for the program there. And what do we have next, Eva, coming up?
Well, we have the awards time. So we, as in every community all hands, we want to thank all of our contributors. I know each and every single one of you, from attending conferences, from organizing meetup groups, writing blog posts, tweeting about the new features at Docker. Everybody is putting effort into the community. However, this time we want to celebrate a few special people that have gone above and beyond, and we just want to mention them by name and to thank them. So I'm going to start with the Open Source Awards. We want to thank Avi Dieter. So thank you so much for helping debugging Docker Desktop, as well as reporting the container deintegration bugs. Thank you, Avi. I know our engineers are always telling us to reach out to you, to thank you for your efforts. And we just want to say that you're a very valuable member of the community. So keep the good work. And again, thank you. And next we have, Alba, what do we have?
Yeah, the community leaders. This time I decided to point out these two people, because I would say that in theory, they have really different backgrounds in our community, I mean, but in the end, they are both awesome community leaders. I would like to start with Shelly Benhoff. She's the community leader from Orlando. And I would like to acknowledge Shelly, shout out to Shelly, because she has joined really recently, a couple months back. And ever since, she has already organized a couple of meetups. She's also the organizer, the person behind Tiaras Tech, which is a podcast in which she interviews underrepresented collectives in tech, especially women. And yeah, she is fantastic. So thank you so much, Shelly, for your contributions to the Community Leaders Program. And the second one would be Catalin Llora. I'm a bit biased with Catalin, I have to say, because he's also based in the Netherlands, as I am. And perhaps because of that, I don't know, I've had the chance of getting in touch with him more often. And I have to say he's an amazing community builder. He has been working within the Dutch ecosystem for years. He's also very big in the Cloud Native Foundation. You can see him very often in these sort of meetups and then conferences. So thank you both. And yeah, thank you so much for all your hard work. And I think we can't finish this without our captains, right? We need to know who are the awarded captains for this 7th edition of the Community All Hands.
Yes, and we have the next. So that's Edith Pugya. She's one of our newest captains, and you just saw her today. She was giving a talk with James, and she has been so far an amazing, amazing captain. She's based in Peru. She has helped us with hosting some Twitter spaces. She's always eager to help, always jumping up at the first opportunity to come and talk at our events. She is especially known for her talks about extensions. So thank you, Edith. And something else to mention is that she is very excited to start working in her local community as well as a community leader in Ayacucho in Peru. She says there's a lot of people there who are eager to learn more about Docker, about technology, and it's just an honor to have her there to bring this knowledge to unrepresented communities. So thank you, Edith, for your work. We're very, very excited to have you. And last but not least, we have also Tobias Fenster. He is a captain in Germany, and you will see him tomorrow in our second day of the Community All Hands. He'll be giving a tutorial on containerizing .NET applications. He is also famous for blogging. You can check out his blog. He has very, very good tutorials that I'm a fan of, especially because he always puts a summary in the beginning. And he always puts examples with pictures. He's such a great, great teacher. And yes, he also has built one extension to calculate the size of an image. So Tobias, thank you so much for being a great captain. And thank you again to all the community for being here. Please remember to apply if you want to become a captain or a community leader, and you could be featured in the next Community All Hands.
And also contribute to the open source ecosystem. And don't forget to reach out to us if you have any questions. Also remember that the event continues tomorrow with a couple of workshops, 3 indeed, if I'm not mistaken. Several workshops that are going to be very interesting, I promise.
Yes.
See you soon.
See you soon. We are going to leave you with Michael. Bye.
Bye.
Hello all, it's me again. Just want to kind of wrap things up again, and again, major shout out to those that have been recognized through our community updates and awards. We couldn't do the things that we do without you. Our community is fantastic, is awesome, and we love you, and we're excited to work with you as much as we do. So to kind of just wrap things up again, Javier's been doing some great work visualizing many of the talks that we've heard throughout the day today, and we'll make his drawings available on our website. So stay tuned on the website. We'll have a link to where you can get those drawings. And then finally, again, just remember to continue to use the hashtag Docker community in order to win some swag from us. And we'll see you back again tomorrow, where we'll pick up and we'll finish off our day tomorrow. Again, thanks all again for joining us, and we'll see you tomorrow. Thanks all.